Hello and welcome. I'm glad you're here. Tonight we're going to explore something vast and strange and quietly beautiful. The future. Not the future of tomorrow's weather forecast or next year's technology releases, but the deep future. The future measured in millions of years, billions of years, timescales so enormous they make human history feel like a single breath. The future of stars and galaxies, of continents drifting and oceans disappearing, of possibilities we can barely imagine. But before we begin this journey together, I want to ask you something. How was your day? Really, how was it? Maybe it was long and exhausting, full of small frustrations and endless tasks. Maybe it was ordinary, unremarkable, the kind of day that blurs into all the others. Or perhaps it was special somehow, touched by moments of unexpected joy. Whatever kind of day you had, I'd love to hear about it. Take a moment, if you'd like, to write about it in the comments section below. And if you enjoy these sleepy explorations through science and wonder, consider subscribing to the channel. It helps me keep creating these quiet journeys for you. So settle in, get comfortable, let your breathing slow. The future isn't going anywhere, or rather, it's going everywhere, unfolding at its own patient pace, whether we're awake to witness it or not. Now let's begin. The James Webb Space Telescope will continue observing the universe's earliest galaxies for at least another decade, each image revealing stars that formed over 13 billion years ago. Right now, floating about 1 million miles from Earth, there's a telescope looking backward through time. Not metaphorically, literally. Every photon it captures has been traveling through space for billions of years, carrying information from an era when the universe was young and strange, and nothing like the cosmos we see today. The James Webb Space Telescope works in infrared light, which means it can see through the cosmic dust that obscures visible light. It can peer into stellar nurseries where stars are being born and look back to the very edges of the observable universe, to galaxies that formed when the cosmos was just a few 100 million years old. These are galaxies we'll study for years to come. Each image a time capsule from an era so distant it challenges our imagination. Think about that for a moment. The light falling on Webb's golden mirrors began its journey before Earth existed, before our sun ignited, before the Milky Way looked anything like it does today. These photons have been traveling through the expanding darkness of space for 13 billion years, just to arrive at precisely the right moment to hit a mirror we built and placed at exactly the right location to catch them. And this telescope will keep working for at least another decade, probably longer, year after year, sending back images of the deep past, of baby galaxies and ancient stars, of a universe we can see but never touch. Each observation is a gift from the distant past, delivered on schedule after an incomprehensibly long journey. It's enough to make you think about patience on cosmic scales, about how some things are worth waiting for, even if the wait is measured in billions of years. By 2030, we'll likely have detailed maps of the ocean floor rivaling our maps of Mars, revealing underwater mountain ranges we've never seen. Here's something strange. We know more about the surface of Mars than we do about the bottom of our own ocean. We've mapped the red planet in remarkable detail, identified ancient riverbeds and towering volcanoes, created topographical maps accurate to within a meter. But more than 80% of Earth's ocean floor remains essentially unknown to us, hidden beneath miles of dark water, as mysterious as any alien world. But that's changing. By the end of this decade, we'll likely have detailed maps of these underwater landscapes. Mountain ranges taller than the Himalayas, canyons deeper than the Grand Canyon, volcanic systems that dwarf anything on land. We'll see the mid-ocean ridges where tectonic plates pull apart and new seafloor is born. We'll trace the underwater rivers of dense, salty water flowing along the ocean bottom. We'll find ecosystems we never imagined, living in darkness and crushing pressure. It's a bit humbling, really. We launch telescopes to study galaxies billions of light years away, but our own planet still holds vast territories we've never truly seen. These underwater mountains have existed for millions of years, completely unknown, patient in their darkness, waiting for the moment when our technology finally becomes sophisticated enough to reveal them. And when we do map them, when we finally see these hidden landscapes in detail, I wonder what we'll find. What mysteries have been resting there, in the deep, in the cold, and the dark? What will we learn about our planet that we should have known all along? The future isn't always about discovering what's far away. Sometimes it's about finally seeing what's been beneath us the whole time. The next total solar eclipse visible from the contiguous United States won't occur until August 2044, a 20-year wait after 2024. There's something about a total solar eclipse that stops time. For a few minutes, rarely more than 7, often much less, the moon passes directly between Earth and the sun, and day becomes a strange twilight. The temperature drops. Birds fall silent, confused. Stars appear in the afternoon sky, and the sun's corona, normally invisible in the glare of daylight, becomes visible as a ghostly halo around the moon's silhouette. If you saw the eclipse in 2024, you're one of the lucky ones. The next total solar eclipse visible from the contiguous United States won't happen until August 2044. 20 years. An entire generation of children will be born, grow up, and approach adulthood in the time between these two events. Eclipses require such precise alignment. The moon must be at just the right distance from Earth, close enough to appear large enough to cover the sun's disk. It must cross the plane of Earth's orbit at exactly the right moment. And the shadow it casts on our planet's surface is tiny, rarely more than 100 miles wide, racing across the landscape at over 1,000 miles per hour. If you're not in the path of totality, you see a partial eclipse at best. The difference between 99% coverage and 100% coverage is the difference between a curiosity and a life-changing experience. These rare alignments remind us that even the most predictable cosmic clockwork requires patience. The universe operates on its own schedule, indifferent to our desire for spectacle. The eclipse will come when it comes, following the ancient mathematics of orbital mechanics, neither early nor late. And those who witness it will carry that memory forever. The day the sun disappeared at noon, the day the universe reminded them of its quiet power. Within the next few years, quantum computers may solve specific problems that would take conventional computers longer than the age of the universe. Quantum computers are strange machines. They don't think the way ordinary computers do. While a conventional computer processes information as bits, ones and zeros, on or off, binary choices made millions of times per second. A quantum computer uses qubits, which can exist in multiple states simultaneously. It's like the difference between flipping a coin and examining the result versus somehow working with the coin while it's still spinning in mid-air. Neither heads nor tails, but both at once. This allows quantum computers to explore many possible solutions to a problem simultaneously, a phenomenon called superposition, for certain very specific types of problems, simulating molecular interactions for drug discovery, optimizing complex logistics, breaking certain types of encryption. They can find answers exponentially faster than any conventional computer could. How much faster? For some problems, a quantum computer might find a solution in hours that would take the best conventional supercomputer longer than the current age of the universe, about 13.8 billion years, to solve. Not days or years, but eons. It's a difference so vast it's almost meaningless, like comparing the blink of an eye to the lifetime of stars. But quantum computers won't replace your laptop. They're highly specialized tools, useful for specific tasks, but useless for checking email or browsing the web. They require temperatures near absolute zero to function, isolation from even the tiniest vibrations, and they're extraordinarily difficult to program. They're not better computers in a general sense. They're different computers, operating on fundamentally different principles, suited for fundamentally different tasks. Still, there's something beautiful about the idea that we're learning to harness quantum mechanics. The strange, probabilistic rules that govern the subatomic world, to solve problems that would otherwise remain forever beyond our reach. We're teaching ourselves to think in quantum terms, to work with uncertainty and superposition rather than fighting against them. And that might be the real revolution, not the computers themselves, but what they teach us about working with reality at its most fundamental level. The Voyager 1 spacecraft, launched in 1977, will continue drifting through interstellar space for billions of years, long after humanity is gone. On September 5th, 1977, we threw a bottle into the cosmic ocean. We call it Voyager 1, and it's now the farthest human-made object from Earth, over 15 billion miles away and still traveling. It's in interstellar space now, beyond the influence of our sun's solar wind, drifting through the space between stars at about 38,000 miles per hour. But speed is relative. In cosmic terms, Voyager is crawling. It won't approach another star for 40,000 years, and even then it will pass by at a distance, a silent visitor glimpsed from afar. It will never land anywhere, never be retrieved. It will simply drift for millions of years, then billions, an eternal traveler in the darkness between suns. Attached to Voyager is a golden record, a literal phonograph record made of gold-plated copper, containing sounds and images from Earth, the song of a humpback whale, a Beethoven symphony, greetings in 55 languages, pictures of humans, animals, landscapes, diagrams of our DNA and our location in the galaxy. It's a message in a bottle, though we have no idea if anyone will ever find it. Long after the sun has exhausted its fuel and swelled into a red giant, consuming the inner planets, Voyager will still be out there, coasting through the dark. Long after whatever comes after humanity, if anything does, Voyager will continue its journey. It might be the longest-lasting remnant of our civilization, this little spacecraft carrying our greetings to whoever or whatever might someday intercept it. There's something both hopeful and melancholy about that, isn't there? This tiny ambassador, representing a species that knew it was temporary, but wanted to say hello anyway. We knew we wouldn't be around to see if anyone responded, but we sent the message regardless. Not because it was practical, but because it felt important to reach out, to say, we were here, we existed, we wondered if you do too. And now Voyager drifts on, patient and silent, carrying that hope into the endless night. By the 2030s, we may have the first permanent human settlement on the moon, with astronauts living in lunar lava tubes for protection. The moon has caves. Deep beneath its dusty surface, there are tunnels formed billions of years ago when molten rock flowed beneath the lunar crust, leaving hollow channels when it drained away. These lava tubes can be enormous. Some might be large enough to contain entire cities, with ceilings hundreds of feet high and lengths stretching for miles. And these caves might become humanity's first permanent home beyond Earth. Living on the lunar surface is dangerous. There's no atmosphere to block radiation from the sun and cosmic rays, no protection from meteorites, which strike the moon's surface constantly, small ones every day, larger ones frequently enough to be a real concern. Temperatures swing from 250 degrees Fahrenheit in sunlight to minus 200 degrees in shadow. But inside a lava tube, you'd have natural protection from all of this. The rock overhead would shield you from radiation and meteorites. The temperature would remain stable at around minus 4 degrees Fahrenheit. Cold, certainly, but consistent, which makes it easier to manage. You could build a habitat inside these ancient caves, pressurize them, live and work protected by billions of years of accumulated lunar rock. By the 2030s, we might see the first crews setting up permanent residence in these underground chambers. They'd be pioneers in the truest sense, living in an environment utterly hostile to human life, utterly dependent on their technology, yet establishing the first human foothold on another world. They'd look up at Earth hanging in their sky, a blue and white marble against the black, and know they were living in a place no human had ever stayed before. It won't be easy. Nothing about living on the moon will be easy, but there's something compelling about using these natural features, these caves created by ancient volcanism, as shelter for humanity's next step into space. We'd be working with the moon rather than against it, finding places where the environment is slightly less hostile, slightly more forgiving. And from that foothold, who knows what might follow? The next time Halley's Comet returns to Earth's skies will be in 2061, continuing its 76-year cycle that humans have documented for over 2,000 years. There's a comet that's been visiting Earth with such regularity that it's part of human history. Halley's Comet, named after Edmund Halley, who first calculated its orbit, appears in our skies roughly every 76 years. It's been recorded in Chinese astronomical records dating back to 240 BCE. It was seen in 1066, depicted in the Bayeux Tapestry as an omen before the Battle of Hastings. Mark Twain was born during its appearance in 1835 and died when it returned in 1910. He had predicted this himself, saying he came in with the comet and would go out with it. The last time Halley's Comet came close to Earth was 1986. If you saw it then, perhaps you were a child, looking up at the night sky with wonder. Perhaps you were already an adult, taking your own children outside to see this visitor from the outer solar system. Or perhaps you weren't born yet, and this piece of cosmic clockwork was ticking away its orbit while you were still decades from existence. The next time it returns will be 2061. If you saw it in 1986 as a child, you might be a grandparent by then. If you're young now, you might see it with your own children or grandchildren someday. It's a marker of human lifespans, this comet, appearing rarely enough that most people only see it once or twice, if they're fortunate. And it will continue this cycle long after we're all gone. In 2061, then 2137, then 2213, circling the sun in its long elliptical orbit, swinging close to Earth every 3/4 of a century, utterly indifferent to human affairs. It's been doing this for millennia before humans existed in any recognizable form, and it will continue for millennia after we're gone. There's something comforting about that kind of constancy, about a cosmic visitor that keeps its appointments with such precision. The universe, for all its chaos, has rhythms you can count on. Antarctica's Thwaites Glacier, often called the Doomsday Glacier, could collapse within decades, but scientists are working to understand its complex dynamics. In West Antarctica, there's a glacier the size of Florida. It's called Thwaites, though it's gained a more dramatic nickname, the Doomsday Glacier. The name comes from what might happen if it collapses. It could raise global sea levels by about 2 feet, and more importantly, its collapse might destabilize other glaciers in West Antarctica, potentially leading to much larger sea level rise over time. But glaciers, despite these dramatic nicknames, don't operate on human timescales. They move slowly, responding to forces we're still working to understand. Warm ocean water circulates beneath Thwaites, melting it from below. The glacier is retreating, but how fast and whether that retreat will accelerate or stabilize is something scientists are actively studying. The future isn't written yet. We're learning about the complex dynamics of ice sheets, how they respond to warming oceans, how bedrock geography affects their stability, how feedback loops can either amplify or dampen changes. Every research expedition to Thwaites reveals new complexity, new factors we hadn't fully considered. And while the name Doomsday Glacier grabs headlines, the reality is more nuanced. Yes, this glacier is changing, and those changes will have consequences. But glacial processes, even accelerated ones, still move at glacial speeds. We have time to study, to understand, to adapt. We have time to make choices that might influence what happens next. There's something almost meditative about the pace of ice. It flows like a very slow river, responding to gravity and temperature and pressure over decades and centuries. Even as it changes, even as it retreats, it does so with a kind of patient inevitability that defies panic. The glacier doesn't hurry. It simply responds to the conditions it encounters, following the physics of ice and water and heat, indifferent to our concerns, but worth our attention nonetheless. The International Space Station will likely be deorbited around 2030, ending over 30 years of continuous human presence in low Earth orbit. For over 2 decades now, there have been humans living in space, not visiting, living. At any given moment since November 2nd, 2000, there have been astronauts aboard the International Space Station, orbiting Earth every 90 minutes, living and working 250 miles above the planet's surface. But nothing lasts forever, not even space stations. The ISS is aging. Its modules were launched between 1998 and 2011, and space is a harsh environment. Radiation, temperature extremes, micrometeorite impacts, the constant stress of pressurization and depressurization. All of these take their toll. Systems need repair. Components wear out. And eventually, around 2030, the decision will likely be made to bring it down. The deorbit will be controlled and careful, using a combination of the station's remaining fuel and possibly additional spacecraft. Mission controllers will lower its orbit gradually, then make a final, targeted re-entry into the Pacific Ocean at Point Nemo, the oceanic point furthest from any land, where several other spacecraft have been deliberately crashed. The ISS will burn up mostly, but some larger pieces will survive to splash down in deep water, far from shipping lanes or inhabited areas. The next Mars opposition, when Earth and Mars are closest together, will occur in 2035, offering the best launch window for interplanetary missions. The planets dance. Not literally, of course, but their movements around the sun create patterns as predictable as any choreography. Earth orbits the sun once every 365 days, while Mars takes 687 days. Because we're moving at different speeds on different orbital paths, the distance between us constantly changes. Every 26 months or so, Earth catches up to Mars in its orbit, and for a brief window, the two planets are as close as they're going to get, somewhere around 35 to 60 million miles apart, depending on where each planet is in its elliptical orbit. We call this opposition when Mars appears opposite the sun in Earth's sky, rising as the sun sets. These oppositions are our best opportunities to send missions to Mars. The journey is shorter, requiring less fuel and less time. Spacecraft launched during opposition windows can reach Mars in 6 to 9 months, rather than the year or more it might take at other times. The difference matters enormously when you're hauling tons of equipment and limited fuel across interplanetary space. The next particularly favorable opposition will be in 2035. Mission planners are already considering it, sketching out trajectories, calculating fuel requirements, designing missions that won't launch for another decade. There's something beautiful about that kind of long-term thinking, preparing now for a launch window that exists because of the orbital mechanics established when the solar system formed 4.6 billion years ago. Mars will be there in 2035, right on schedule, swinging close to Earth as it has countless times before. And if we're ready, if we've done our planning and built our spacecraft and trained our crews, we'll be able to take advantage of this celestial alignment. The universe provides the opportunities. Whether we seize them is up to us. Within a few decades, we might develop living buildings made from engineered bacteria that grow, self-repair, and respond to environmental conditions. Imagine a building that heals itself when damaged. Not through human intervention, but autonomously. The way your skin closes a small cut without you having to think about it. A crack appears in a wall, and specialized bacteria living within the material detect it, migrate to the damage, and begin producing limestone or other minerals, filling the gap. This isn't science fiction. Researchers are already working on bioengineered materials that incorporate living organisms, bacteria, fungi, even algae, into construction materials. These organisms could serve multiple functions. Some bacteria can produce calcium carbonate, essentially making limestone to fill cracks. Others might generate bioluminescence, creating buildings that glow softly at night without electricity. Still others could absorb CO2 from the atmosphere or purify water. The buildings wouldn't be alive in the way we usually think of it, but they'd be living in the sense that they'd contain active biological components, constantly responding to their environment. A wall might become more porous in hot weather to improve ventilation, then seal itself when temperatures drop. Foundations might strengthen themselves over time rather than weakening. There are challenges, of course. Keeping bacteria alive long-term in building materials isn't trivial. You need to provide them with nutrients, maintain appropriate moisture levels, ensure they don't die off or mutate in unexpected ways. But within a few decades, we might see the first commercial buildings incorporating these technologies. It would change our relationship with architecture. Buildings wouldn't be static objects anymore, but dynamic systems, more akin to ecosystems than engineering projects. We'd be working with biology rather than just physics and chemistry, growing structures rather than merely building them. And perhaps that's appropriate. After all, humans have been living in structures built by living organisms for millennia. We just called them caves and trees and shells. Maybe we're simply coming full circle, using new tools to recapture old wisdom. The global human population will likely peak around 2086 at approximately 10.4 billion people, then gradually decline. For most of human history, our population has been growing. Slowly at first, it took until 1804 to reach 1 billion people. Then faster, the second billion by 1927, the third by 1960. The growth seemed exponential, unstoppable, a curve shooting upward toward some unimaginable future. But curves don't rise forever. Demographic models suggest that global population will likely peak sometime around 2086 at roughly 10.4 billion people. After that, it will begin a slow decline, not because of catastrophe, but because of something far more subtle: choices. As societies develop, birth rates fall. This has happened in nearly every industrialized nation. People have fewer children when they have access to education, healthcare, and economic opportunities. When child mortality is low, there's less pressure to have many children to ensure some survive. When women have career options and control over their reproduction, family sizes shrink. This demographic transition has already happened in much of Europe and East Asia. Japan's population is declining. Germany's would be too, without immigration. South Korea has one of the lowest birth rates in the world. The transition is now happening in much of the developing world as well. So the models suggest a peak, not a plateau, but an actual maximum, followed by gradual decline. The human population might be smaller in 2150 than in 2086, smaller in 2200 than in 2150. Not catastrophically smaller, just smaller. Fewer of us spread across a planet that might feel a bit less crowded. It challenges our assumptions about growth as destiny. We've become accustomed to the idea of more people, more cities, more of everything. The idea of less, of deliberately smaller populations choosing different balances between work and life, between consumption and sustainability, feels almost radical. But it might be our future, not imposed by disaster but chosen through millions of individual decisions, adding up to a species that decides, collectively and unconsciously, that there's a right size for humanity after all. By 2040, we may see the first commercial fusion reactor providing clean energy to a power grid, fulfilling a dream pursued since the 1950s. The sun is a fusion reactor. At its core, hydrogen atoms crash together under immense pressure and temperature, fusing into helium and releasing tremendous amounts of energy in the process. This has been happening for about 4.6 billion years, and it will continue for another 5 billion or so. The sun is very good at fusion. Humans have been trying to replicate this process in controlled conditions since the 1950s. We can do fusion. We've achieved it in laboratories many times. The challenge is making fusion that produces more energy than it consumes to initiate and sustain the reaction. We need to heat plasma to temperatures exceeding 100 million degrees Celsius, contain it with powerful magnetic fields, and keep it stable long enough for fusion to occur efficiently. For decades, fusion power has been 30 years away, a perpetual promise that never quite arrives. But recently, things have changed. In 2022, researchers at the National Ignition Facility achieved fusion ignition, a reaction that produced more energy than the lasers put into it. Not yet more than the entire facility used, but a crucial milestone nonetheless. Private companies are now racing to develop commercial fusion reactors, and some are projecting the first grid-connected fusion power plant by the late 2030s or early 2040s. Whether they'll meet these timelines remains uncertain, but there's genuine momentum now, a sense that fusion might finally transition from perpetual future to actual present. If it works, and that's still a meaningful if, fusion could provide enormous amounts of clean energy. The fuel is abundant. Deuterium can be extracted from seawater, and tritium can be bred from lithium. The waste is far less problematic than nuclear fission. There's no risk of meltdown or runaway reaction. It's the dream of bottled stars, of carrying a piece of the sun's power generation down to Earth and putting it to work. We've dreamed this dream for 70 years now, through setbacks and slow progress and occasional breakthroughs. Maybe in another 20 years, that dream finally becomes routine reality. Maybe fusion joins the long list of technologies that seemed impossible until suddenly they weren't. The next great American eclipse crossing the entire continental U.S. won't happen until 2045, making each solar eclipse a once-in-a-generation event. There's something about totality that photographs can't capture. People try. They stand with cameras and phones, capturing the sun's corona, the diamond ring effect, the strange quality of light during those few minutes when the moon completely covers the sun. But the images never quite convey what it feels like to be there, to experience it directly. The 2024 eclipse crossed the United States from Texas to Maine, and millions of people traveled to be in the path of totality. Those who were there talk about the sudden temperature drop, the way shadows became strange and sharp, the 360-degree sunset as the moon's shadow raced across the landscape at over 1,100 miles per hour. They talk about stars appearing in the afternoon sky, about birds falling silent, about a profound sense of cosmic alignment. The next total solar eclipse to cross the entire continental United States won't happen until 2045, 21 years away. If you were a child in 2024, you'll be approaching middle age. If you were middle-aged, you'll be in your senior years. An entire generation will grow up in the gap between these two events. And this rarity is intentional, a consequence of orbital mechanics and probability. Total solar eclipses happen somewhere on Earth roughly every 18 months, but any given location sees one only about once every 375 years on average. The United States has been extraordinarily fortunate to have two in less than a decade, first in 2017 and then 2024. That good fortune won't repeat for another generation. So those who saw totality in 2024 are lucky. They witnessed something that won't return to their part of the world for decades. An alignment of sun and moon and earth so precise that being a few miles outside the path of totality means missing it entirely. The difference between 99% coverage and 100% coverage is the difference between "that's interesting" and "I understand why ancient peoples thought this was a message from the gods." The universe doesn't perform on demand. It follows its own schedule, and sometimes that schedule requires patience measured in decades. The eclipse will come again, right on time, neither early nor late. And those who witness it will join the long line of humans throughout history who have stood in the moon's shadow and felt very small and very fortunate. By 2100, sea levels are projected to rise between 0.3 to 1 meter, but the exact amount depends on choices we make now. The future isn't a single destination, but a probability cloud, a range of possibilities that narrows as we move through time and make choices. Sea level rise is one of the clearest examples of this. We know the oceans are rising, about 8 to 9 inches since 1880, with the rate accelerating. We know they'll continue rising, but how much depends on variables we're still influencing. The projections for 2100 range from about 1 foot to over 3 feet, depending on emissions scenarios, ice sheet dynamics, and factors we're still working to understand. That might not sound dramatic, but consider what it means. A meter of sea level rise would permanently flood areas where tens of millions of people currently live. Low-lying island nations would become uninhabitable. Major coastal cities would require massive infrastructure investments in barriers and pumping systems. But here's what's interesting. The future isn't predetermined. The range exists because our choices matter. Lower emissions scenarios produce less warming, which produces less sea level rise. It's not binary. We're not choosing between fine and catastrophe. We're choosing where in the range we'll end up, shading the future darker or lighter through countless decisions made across decades. There's something both daunting and empowering about that. Daunting because we can't simply relax and let things work out. The trajectory isn't automatically benign, but empowering because we're not helpless observers of an inevitable future. We're participants, shapers, our collective choices literally determining what the coastlines will look like in 2100. The ocean is patient. It responds to heat content and ice melt with a certain unhurried inevitability. But it's not malicious or even indifferent. It's just following the physics of thermal expansion and water flowing to its lowest level. What we do now influences what happens then. The future is being written in the present, one decision at a time, accumulating like water seeking its level. The first humans born on Mars might develop slightly different skeletal structures due to the planet's lower gravity, about 38% of Earth's. Imagine being born in a place where gravity pulls at you with only about a third of the force you'd experience on Earth, where jumping is easier, falling is slower, and your body doesn't have to work as hard to stand upright or pump blood to your brain. This is what it would be like for children born on Mars. Gravity shapes us. Our bones grow dense and strong because they have to support our weight against Earth's pull. Our muscles develop to lift and move in 1g acceleration. Our cardiovascular system is designed to push blood upward against gravity's resistance. But on Mars, with gravity only 38% as strong, these stresses would be reduced. Children born and raised on Mars would likely develop differently. Their bones might be less dense, not because of disease, but because they simply don't need the same structural strength. They might grow taller. With less gravitational compression, the spine could elongate more. Their muscles might be less bulky, but optimized for Martian conditions. And here's the concerning part. They might never be able to visit Earth comfortably. Imagine growing up in gentle Martian gravity, your skeleton and muscles perfectly adapted to that environment, then trying to function in Earth's gravity field. It would be like an Earth human trying to function in a place with 2.6 times normal gravity. Everything would feel crushing. Standing would be exhausting. Your heart would struggle to pump blood. Your bones might be too fragile to support your own weight. So the first generation of Mars-born humans might be permanently Martian, not just culturally or by citizenship, but physiologically. Human beings who could look at Earth in their sky and know they could never comfortably visit the world their parents came from. They'd be a new branch of humanity, diverging from their Earth cousins not through millions of years of evolution, but through the simple fact of growing up in different gravitational fields. It raises profound questions about what it means to be human, about how much our environment shapes us, about whether we remain one species if we're scattered across worlds with radically different conditions. But perhaps that's the future of humanity, not just one species on one world, but variations on a theme, each adapted to their home while sharing a common origin story written on Earth. In about 50,000 years, the star Gamma Cephei will replace Polaris as Earth's North Star due to our planet's axial precession. Right now, if you're in the northern hemisphere and you want to find north, you look for Polaris, the North Star. It sits almost directly above Earth's North Pole, appearing to remain stationary while all other stars wheel around it throughout the night. Navigators have used it for centuries, a fixed point in the turning sky, reliable and constant. But Polaris won't always be the North Star. Earth's axis doesn't point in exactly the same direction all the time. Like a spinning top that wobbles as it slows, Earth's axis traces out a slow circle in space, a phenomenon called precession. This circle takes about 26,000 years to complete. As Earth's axis slowly shifts, different stars align with our North Pole. About 5,000 years ago, the pole star was Thuban in the constellation Draco. Ancient Egyptians built the pyramids aligned to Thuban. In another 12,000 years, brilliant Vega will be the pole star, far brighter than Polaris is today. And in about 50,000 years, a star called Gamma Cephei will take its turn. There's something quietly profound about this. We think of the North Star as eternal, fixed, unchanging. We use true north as a metaphor for constancy and reliability. But even this apparently fixed point is temporary, part of a slow cosmic dance that predates human civilization and will continue long after we're gone. The stars we call fixed are wandering. The constellations are gradually distorting as stars drift in their orbits around the galaxy. The pole star changes with the millennia. Even the celestial coordinates we use to map the sky need updating every few decades. Nothing is truly fixed. Everything is in motion, changing at speeds ranging from imperceptible to dramatic, depending on your perspective and timescale. But the journey continues. Polaris will serve as our North Star for many more centuries, patient and bright, before passing the duty to another star. And in about 26,000 years, having traced its full circle, Earth's axis will point back toward Polaris again, and it will reclaim its ancient role. The wheel turns, the dance continues, and the only constant is change itself. Future archaeologists might identify our era as the plastic layer in geological strata, a thin band marking the Anthropocene epoch. Millions of years from now, if there are geologists studying Earth's rocks, they'll be able to identify our time with remarkable precision. Not because of our cities, those will erode. Not because of our monuments, they'll crumble. But because of something far more mundane: plastic. Plastic doesn't biodegrade, not really. It breaks down into smaller pieces, but the polymers themselves persist. Every plastic bottle, every shopping bag, every piece of packaging we've produced since the 1950s is still here somewhere, in some form. Much of it has made its way into sediments, ocean floors, lake beds, floodplains, where it's being gradually buried and compressed, along with everything else that settles out of water. Future geologists might find a distinctive layer in the rock record, a thin band enriched with plastic microparticles, radioactive isotopes from our nuclear tests, and chemical markers of our industrial processes. This layer would be remarkably synchronous across the planet, appearing at the same time level in sediments everywhere, marking the moment when one species gained the ability to leave a permanent geological signature. They might call it the Anthropocene, the human epoch. And its boundary marker wouldn't be bones or artifacts, but the chemical and physical traces of our industrial civilization. Plastic would be the most visible component, a material that didn't exist in nature before we invented it, now embedded in the geological record like the iridium layer that marks the asteroid impact that ended the dinosaurs. There's something humbling about this. We think of ourselves as temporary, our lives measured in decades, our civilizations in centuries or millennia. But our trash is eternal, at least on human timescales. Long after our buildings have weathered away, long after our languages are forgotten, the plastic will remain, a thin but indelible line in Earth's strata. It's not the legacy most of us would choose, but perhaps it's honest. We were here. We made things. We changed the planet in ways that will remain detectable for millions of years. Whether future species find that layer and puzzle over what kind of creatures would wrap everything in polymers, we'll never know. But the evidence will be there, patient and permanent, waiting to tell its story. The next ice age is due based on Earth's natural cycles, but human-induced warming may delay it by tens of thousands of years. Earth has a rhythm. Over the past 2.6 million years, the planet has cycled between ice ages and warmer interglacial periods, driven by subtle changes in Earth's orbit and axial tilt. These changes, called Milankovitch cycles, alter how much sunlight reaches different parts of the planet at different times of year. When the geometry is right or wrong, depending on your perspective, ice sheets grow from the poles, spreading across continents, locking up so much water that sea levels drop by hundreds of feet. The current interglacial period, the Holocene, has lasted about 11,700 years. Based on orbital mechanics, the next ice age should begin within the next few thousand years. Or at least it would if we weren't here. But we've changed the equation. By releasing hundreds of billions of tons of CO2 into the atmosphere, we've increased the greenhouse effect enough that the next ice age might be delayed by 50,000 years or more. We've become a geological force strong enough to override the Milankovitch cycles, to postpone or possibly prevent the next advance of continental ice sheets. This is simultaneously remarkable and unsettling. Remarkable because it demonstrates the sheer magnitude of human influence on planetary systems. We're literally postponing ice ages. Unsettling because it wasn't intentional, wasn't planned, and the consequences extend far beyond our ability to predict or control. In a strange way, we've bought ourselves time. Without our interference, ice sheets might already be beginning their slow advance from the Arctic, creeping southward at a few meters per year, eventually covering much of North America and Europe under kilometers of ice. That's not happening now. Won't happen for tens of thousands of years if current trends continue. But it's worth remembering that ice ages, for all their drama, are natural. They've been happening for millions of years. They're part of Earth's rhythm, neither good nor bad, just different. By preventing the next one, we're not necessarily improving the planet. We're just changing it in ways that benefit our current civilization, while making it less predictable for whatever comes after. The climate isn't fragile. It can't break, but it can change. And when it changes, ecosystems must adapt or relocate or perish, including human ecosystems. We've become powerful enough to delay ice ages, but we haven't become wise enough to fully understand what that means for the deep future. The ice will wait. The orbital cycles will continue. And one day, perhaps 50,000 years from now, the ice age we've postponed might finally arrive. By the late 21st century, we might have digital consciousness preservation, allowing people to upload personality matrices before death. What makes you, you? Is it your memories, the accumulated experiences of a lifetime, your personality, the patterns of thought and reaction that make you distinct? Or is it something else, something ineffable that couldn't possibly be captured in data? By the end of this century, we might be able to test this question. Technologies are being developed that could map neural connections, record personality patterns, preserve memories in digital form. The idea is to create a comprehensive model of a person's mind, not a copy of the brain itself, but the patterns it creates, the information it processes, the self it generates. Whether this constitutes actual consciousness is the question that keeps philosophers awake at night. If we create a perfect simulation of your mind, complete with all your memories and personality traits, is that you? Or is it just an elaborate echo, something that acts like you but isn't actually you? Would the original you experience continuity, or would you simply die while a very convincing copy takes your place? We don't know. We might never know with certainty, because consciousness is subjective. There's no way to verify from the outside whether something is truly experiencing or just simulating experience convincingly. But the technology might arrive regardless of whether we've answered the philosophical questions. People facing terminal illness might choose preservation, hoping that whatever emerges on the other side is close enough to count. Families might keep digital versions of loved ones, finding comfort in conversations with patterns trained on years of recorded speech and behavior. It changes what death means. Not erasing it entirely, the body still fails, the biological substrate still ends, but perhaps creating something that persists beyond, something that carries forward at least part of what made someone who they were. Whether that's immortality or just a sophisticated memorial, each person will have to decide for themselves. The next supercontinent, tentatively named Pangaea Ultima, will form approximately 250 million years from now, as Earth's tectonic plates continue their slow dance. The continents are moving. Right now, this moment, North America is drifting away from Europe at about the same rate your fingernails grow, roughly 2.5 centimeters per year. The Atlantic Ocean widens. The Pacific shrinks. India continues pushing into Asia, raising the Himalayas incrementally higher. Australia migrates northward toward Indonesia. This isn't new. Continents have been drifting for billions of years, driven by convection currents in Earth's mantle. About 300 million years ago, all the continents were assembled into one massive landmass called Pangaea. Before that, there was Rodinia. Before that, Columbia. The continents join and separate in cycles lasting hundreds of millions of years, and they'll join again. In approximately 250 million years, current projections suggest the continents will merge into a new supercontinent. Scientists have tentatively named it Pangaea Ultima, though Novo Pangaea and Amasia are also proposed names, depending on exactly how the collision unfolds. The configuration is still uncertain. Tectonic motion is complex and chaotic enough that predictions become fuzzy over such time scales. But the general pattern seems clear. The Atlantic will eventually stop widening and begin closing. The Americas will drift back toward Africa and Europe. Antarctica will move northward. And over tens of millions of years, the continents will crunch together, raising new mountain ranges, creating a single vast landmass surrounded by a single global ocean. The climate of Pangaea Ultima will be extreme. The interior, far from any ocean, will be desert, blazing hot in summer, frigid in winter, with little moderating influence from water. Coastal regions might be more habitable, but monsoons could be fierce and unpredictable. Of course, none of this matters to us directly. 250 million years is an incomprehensible span of time. Mammals didn't exist 250 million years ago. The ancestors of all mammals, birds, and dinosaurs were still small reptiles sharing the world with early archosaurs. Whatever exists on Earth in another 250 million years will be so different from us that the word descendant barely applies. But the dance continues. The plates drift. The continents gather and scatter like dancers at a ball that's been going on for billions of years and will continue for billions more. Pangaea Ultima will form, persist for 100 million years or so, then break apart again. And the cycle will continue until the Earth's core finally cools enough that the mantle stops convecting and the dance finally, slowly, comes to rest. Within a century, we may develop programmable matter, materials that can change shape, properties, and function on demand. Imagine a substance that could be a chair when you need to sit, then flow and reform into a table when you need a surface. That could be rigid when supporting weight, but soft when you fall against it. That could conduct electricity or insulate against it, be transparent or opaque, rough or smooth, all depending on what you needed in that moment. This is the promise of programmable matter, materials composed of tiny units that can rearrange themselves, changing the bulk properties of the substance. Think of it like pixels on a screen, but in 3 dimensions and with physical properties. Each tiny unit could move, connect to neighbors, change its state, all coordinated to create whatever macroscopic form and function you desired. The technology is still primitive. Researchers have created simple systems using small robots that can link together in different configurations, or materials with shape memory properties that respond to temperature or electric fields. But these are proofs of concept, demonstrations that the principles work, not yet practical implementations. Within a century, though, we might have true programmable matter. It would revolutionize manufacturing. Instead of building different objects, you'd just reconfigure the same material. It would change architecture. Buildings could adapt their layout to changing needs. A house could reconfigure itself. More bedrooms when you have a growing family. More open space when the children leave. Accessibility features as you age. There's something almost magical about it. This idea of matter that obeys intention rather than fixed form. But it's not magic. It's engineering at increasingly small scales, creating materials that are less like traditional objects and more like frozen liquids, ready to flow into new configurations when prompted. Of course, it raises questions. If objects can change form instantly, what happens to craftsmanship, to permanence, to the idea of objects having histories and character? But perhaps those are the wrong questions. Perhaps programmable matter doesn't replace traditional materials, but supplements them, offering a different kind of utility for different needs. The future rarely replaces the past completely. More often, it just adds new options to the available palette. The Arecibo message we sent to space in 1974 will reach its target star cluster M13 in about 24,176 years, and any reply would take just as long to return. In 1974, we aimed a radio telescope at a cluster of stars and sent a message. It was brief, only 1,679 binary digits, but encoded within those bits was information about humanity, our DNA structure, our biochemistry, our population, our location in the solar system. We broadcast this at the dedication ceremony of the upgraded Arecibo telescope, sending it toward M13, a globular cluster about 25,000 light-years away, containing hundreds of thousands of stars. That message is still traveling. It's been moving through space at the speed of light for nearly 50 years now, which means it's covered about 50 light years, about 0.2% of the journey. It won't reach M13 for another 24,926 years or so. And if anyone there receives it, understands it, and sends a reply, that reply won't reach Earth for another 25,000 years. The round-trip time for this conversation is approximately 50,000 years. To put that in perspective, 50,000 years ago, Homo sapiens were still sharing the planet with Neanderthals. Cave paintings were cutting-edge technology. Agriculture wouldn't be invented for another 40,000 years. We sent the message anyway, not because we expected a reply in any reasonable time frame, but because it felt important to reach out, to say hello into the vast darkness. It was a symbolic gesture more than a practical communication attempt, a way of marking a milestone in our development as a technological species. And now that message travels on, expanding as it goes, becoming fainter and more diffused, but never stopping. Even if Arecibo itself is gone, the telescope collapsed in 2020, the signal continues. In 24,026 years, it will wash over M13 like a whisper. Maybe someone will hear, maybe they'll understand, maybe they'll reply, or maybe not. Maybe the message will pass through the cluster unnoticed, continuing on into the deeper void beyond, traveling for millions or billions of years. An artifact of a species that once looked up and wondered if anyone else was out there. Either way, it's out there now, permanent and patient, carrying our greeting into the deep future. Future humans might routinely live past 120 years as we better understand cellular senescence and develop targeted aging interventions. Human lifespan has increased dramatically over the past century, not because our maximum age has changed, but because more people survive to reach it. Infant mortality has plummeted. Infectious diseases are controllable. Accidents are less fatal. The result is that many more people reach their 70s, 80s, 90s. But there seems to be a limit. The oldest verified person, Jean Calment, lived to 122. A handful of others have reached 117, 119. But despite all our medical advances, no one reliably lives past 120. There appears to be a biological ceiling, something fundamental about how our cells age, that creates a maximum lifespan. That ceiling exists because our cells have built-in aging mechanisms. Telomeres shorten with each division. DNA accumulates damage. Proteins misfold. Cellular cleanup processes become less efficient. Eventually, cells either die or become senescent. Zombie cells that don't function properly but don't die either, just sit there secreting inflammatory factors that damage neighboring cells. But these mechanisms aren't mysterious anymore. We understand them increasingly well, and understanding creates the possibility of intervention. Scientists are developing therapies to clear senescent cells, to restore telomere length, to repair DNA damage, to boost cellular maintenance systems. Within this century, we might see interventions that don't just extend lifespan, but extend health span, the period of life spent in good health. The goal isn't necessarily to live to 150, but to compress the period of decline into a much shorter window at the end of life. Instead of spending years in gradual deterioration, you might remain healthy until your late hundreds, then decline relatively quickly. This wouldn't be immortality, just a longer, healthier span before the inevitable end. Whether that's desirable is a different question. Longer lives might mean longer careers, delayed retirement, more generations alive simultaneously. Society would need to adapt in ways we haven't fully considered. But the biology increasingly seems tractable. We're not fighting entropy itself, just the specific mechanisms by which our bodies succumb to it. And those mechanisms, while complex, are not infinitely complex. They can be understood, and what can be understood can potentially be modified. The Pacific Ocean is slowly shrinking at about 2 to 3 centimeters per year as tectonic plates converge, eventually closing entirely. The Pacific Ocean is dying. Not quickly. This is geology, after all, where quickly is measured in millions of years, but it's shrinking, narrowing by a few centimeters annually as the tectonic plates beneath it converge. Around the Pacific's edges, oceanic crust is being pushed beneath continental plates in a process called subduction. The Nazca Plate slides under South America. The Pacific Plate dives beneath Japan. All around the Ring of Fire, the ocean floor is descending into Earth's mantle, being recycled into molten rock, disappearing. Meanwhile, the Atlantic Ocean is widening. Iceland literally splits wider every year as new seafloor is created at the mid-Atlantic ridge. The Americas drift away from Europe and Africa. The Atlantic grows while the Pacific shrinks. Eventually, in 200 to 300 million years, the Pacific might close entirely. The Americas could collide with Asia, crumpling up massive mountain ranges, creating a configuration where most land is joined into one supercontinent, with a single vast ocean on the other side. It's happened before. Oceans open and close over hundreds of millions of years. The Atlantic Ocean is relatively young, only about 180 million years old. Before it opened, there was a previous ocean, Iapetus, that closed when Pangaea formed. The Mediterranean is a remnant of Tethys, a much larger ocean that once separated Gondwana from Laurasia. Oceans are temporary. They seem eternal from a human perspective, vast, ancient, unchanging. But on geological timescales, they're transient features, opening and closing like gaps in a dance floor, where continents waltz past each other. The Pacific has existed for at least 750 million years in some form, making it the oldest current ocean. But even ancient things end. The seafloor sinks back into the mantle. The ocean narrows, and eventually, perhaps 200 million years from now, the last of the Pacific's waters will be squeezed out as continents collide, creating new mountains where an ocean once existed. Nothing lasts forever, not even the largest ocean on Earth. By 2200, we might have permanent settlements in the asteroid belt, mining resources in microgravity environments. Between Mars and Jupiter, there's a belt of rocky debris left over from the solar system's formation. Millions of asteroids ranging from Pebbles to Ceres, which is nearly 600 miles across. For most of human history, these were just points of light, curiosities noted by astronomers. But they represent something else, resources. Some asteroids are metallic, rich in iron, nickel, platinum group metals. A single metallic asteroid could contain more precious metals than humanity has mined throughout its entire history. Other asteroids are carbonaceous, containing water ice, organic compounds, volatiles that could be processed into fuel and life support. By the late 22nd century, we might have permanent mining settlements in the asteroid belt, not on the asteroids themselves, Most are too small to have meaningful gravity. But in rotating habitats nearby, cylindrical stations spinning to create artificial gravity where miners would live and work. Mining in microgravity would be strange. No need for structural support. Rocks don't fall. No need for heavy equipment. A gentle push can move tons. But also new challenges. How do you anchor yourself while working? How do you prevent fine dust from coating everything? How do you separate materials without gravity to help? These settlements would be truly independent from Earth in ways orbital stations never could be. They'd have local resources, metals to build with, water for life support, materials to process into fuel. They'd be weeks or months away from Earth, too far for easy resupply. They'd develop their own cultures, their own ways of doing things, adapted to life in perpetual freefall, with Earth just a bright star in the sky. It's a vision of a spacefaring future that doesn't require faster-than-light to travel or exotic technologies, just patient engineering applied over decades, gradually expanding human presence into the solar system. The asteroid belt isn't a destination for tourists. It's a place for miners and engineers, for people willing to live in rotating cylinders surrounded by vacuum, extracting resources from airless rocks. But it's achievable with extensions of current technology. The question isn't whether we can, but whether we will. The next time the inner planets align favorably for a Grand Tour spacecraft mission won't occur for another 175 years. The Voyager missions took advantage of something extraordinary, a rare alignment of the outer planets that happens only twice every 175 years. By carefully planning their trajectories, NASA engineers were able to send Voyager 1 and 2 past Jupiter, Saturn, Uranus, and Neptune using gravitational assists, where each planet's gravity accelerated the spacecraft and bent its path toward the next target. Without this alignment, visiting all 4 outer planets would require either multiple separate missions or enormous amounts of fuel. But during the alignment, gravity does the work. Each flyby accelerates the spacecraft, essentially giving it a free speed boost while simultaneously changing its direction toward the next planet. The last favorable alignment was in the late 1970s, which is why the Voyager spacecraft launched in 1977. The next comparable alignment won't occur until the 2150s, about 175 years from the last one. That's too far away to plan for currently. We don't know what technology will be available, what missions will be priorities, even whether humans will still be interested in exploring the outer solar system with robotic probes. But the celestial mechanics don't care about our priorities. The planets will align according to the laws of orbital motion established when the solar system formed. The opportunity will arrive whether we're ready or not. There's something beautiful about the patience required here. The Voyager team knew they were taking advantage of a once-in-a-lifetime opportunity, literally more than a lifetime. None of the engineers who planned those missions will be alive for the next alignment, but they planned anyway, built the spacecraft anyway, launched them into that perfect geometric configuration anyway. The planets dance their slow dance, and we can either choreograph our missions to match their rhythm or watch the opportunity pass by. The next alignment will come in the 2150s, right on schedule. Whether we're there to meet it is up to us. Future geneticists may resurrect extinct species like woolly mammoths using preserved DNA and modern elephant surrogates. In the Siberian permafrost, there are frozen mammoths, not fossils, actual mammoths, preserved by the cold for tens of thousands of years, their DNA still partially intact. Not perfect. DNA degrades even in ice, but usable, readable, potentially editable into something living. The idea is called de-extinction, and mammoths are the poster child. We'd take DNA from frozen mammoth tissue, use it to guide edits to elephant DNA. Elephants are the mammoth's closest living relatives. Then implant the resulting embryo into an elephant surrogate. If it works, the birth would be an elephant-mammoth hybrid initially. But with successive generations and more edits, we could potentially create something genetically very close to a true mammoth. But should we? The mammoths died out about 4,000 years ago, when the last population on Wrangel Island finally succumbed. The world they lived in is gone. The ecosystems they were part of have moved on. Bringing them back wouldn't restore the Pleistocene. It would just drop mammoth-like creatures into a world that no longer has a place for them. And there are practical questions. Where would they live? Who would care for them? What obligations would we have to these resurrected creatures? We'd be bringing them back into a world warmer than they evolved for, potentially sentencing them to struggle in environments they're poorly suited for. Still, the technology edges forward. Advances in genetic engineering make de-extinction increasingly feasible. Whether it's wise is a separate question from whether it's possible. Perhaps the real value isn't in actually creating mammoths, but in developing the techniques. The same tools that could resurrect extinct species could help preserve endangered ones, increase genetic diversity in threatened populations, repair damaged ecosystems. De-extinction technologies might be more useful for preventing extinction than reversing it. But the mammoths wait in the permafrost, frozen in time, their DNA a library we're learning to read. Whether we choose to revive them or simply learn from them, they're teaching us about our power over life and death, about the responsibilities that come with godlike technologies. In approximately 400 years, the star Gliese 710 will pass through the Oort cloud, potentially sending comets cascading toward the inner solar system. Most stars never come particularly close to our solar system. The distances between stars are so vast that near misses are rare events. But in about 1,400 years, a star called Gliese 710 will pass through the Oort cloud, the distant sphere of icy bodies surrounding our solar system, coming within about 0.2 light-years of the Sun. That might not sound close, but in astronomical terms, it's intimate. The star won't hit anything. Space is mostly empty, after all, but its gravity will disturb the orbits of countless Oort cloud objects, giving some of them nudges that send them falling inward toward the inner solar system. The result could be a comet shower lasting thousands of years. Not a disaster. The increased rate would still mean years or decades between individual comet appearances. But astronomers of that era would see more comets than usual, visitors from the distant reaches of the solar system, disturbed by a stellar interloper's gravity. This has happened before. Stellar near misses occur every few million years, They're part of the background dynamics of living in a galaxy where stars drift in their orbits, sometimes passing close enough to gravitationally interact. Most of the time, nothing dramatic happens. Occasionally, we get a period of enhanced comet activity. In 1,400 years, humanity will either be extinct, radically transformed, or spread across the solar system, possibly all three. But whatever we've become, our descendants might look up and see more comets than their history records, ghostly visitors from the solar system's edge, sent inward by the gravity of a passing star. It won't be catastrophic. Just a reminder that our solar system isn't isolated, that we live in a dynamic neighborhood where the neighbors occasionally drift close enough to rearrange the furniture. By the 23rd century, we might develop neural lace, technology allowing direct brain-to-computer interfaces without invasive surgery. Your brain generates electrical signals, billions of neurons firing in patterns that create thoughts, memories, sensations. Right now, to read those signals in detail, we need electrodes placed directly on or in the brain, requiring surgery that carries risks and complications. But researchers are working on less invasive approaches. Neural lace is a concept involving ultra-thin mesh electronics that could be injected through blood vessels, unfurling inside the brain to create a distributed interface with neural tissue. Or perhaps external devices sensitive enough to read brain activity through the skull with unprecedented precision. By the 23rd century, we might have brain-computer interfaces as seamless as putting on headphones. Think a command, and your computer executes it. Imagine a scene and it appears on your screen. Access information directly, as if remembering it, without having to look it up. This would change how we interact with technology fundamentally. No more keyboards, mice, touchscreens, just intention flowing directly into action. You could communicate complex ideas without language, sharing experiences and sensations rather than descriptions of them. But it raises profound questions about privacy and identity. If your thoughts can interface with computers, can they be read without permission? Could malware affect your cognition? Where does your mind end and the technology begin? These aren't just hypothetical concerns. Any technology that bridges brain and computer must address security, consent, and the potential for misuse. The benefits could be extraordinary, restoring communication to those who've lost it, enhancing cognitive abilities, enabling new forms of creativity. But the risks are equally significant. The technology edges forward slowly. Current brain-computer interfaces can do remarkable things, allowing paralyzed people to control robotic arms, enabling communication through thought alone. But they're still primitive, requiring surgery, providing limited bandwidth, prone to degradation over time. 2 more centuries might give us what we need: materials that interface seamlessly with neural tissue, signal processing sophisticated enough to decode intention reliably, and ethical frameworks for managing technology that literally reads minds. Whether we'll be wise enough to use it well is another question entirely. The Amazon rainforest could transition to savanna within 50-100 years if current deforestation rates continue, though restoration efforts might prevent this. Rainforests create their own weather. The Amazon's trees release so much water through transpiration that they generate clouds, which produce rain, which feeds the trees. It's a self-sustaining cycle, but only up to a point. Remove enough trees, and the cycle breaks. Scientists estimate there's a tipping point somewhere between 20 to 25% total deforestation. We're currently around 17%. Beyond that threshold, the remaining forest might not generate enough moisture to sustain itself. The rain would decrease. Dry seasons would lengthen. Trees adapted to constant moisture would die, replaced gradually by savanna grasses and scattered drought-resistant trees. This wouldn't happen overnight. The transition would take decades, creeping across the landscape as local rainfall patterns shifted. But once started, it might become self-reinforcing. Less forest means less rain means conditions that favor savanna over forest. The consequences would extend far beyond the Amazon. The rainforest is a massive carbon sink, storing carbon that would otherwise accelerate warming. It influences weather patterns across South America and beyond. It harbors perhaps 10% of Earth's species, most found nowhere else. But the future isn't written. Deforestation rates have fluctuated over time, decreasing dramatically in the mid-2000s before rising again. Restoration efforts are underway, replanting degraded areas, protecting remaining primary forest, working with indigenous communities who've stewarded these lands for millennia. Ecosystems have tipping points, thresholds where gradual changes suddenly accelerate. But these thresholds work both ways. The same feedback loops that could drive collapse could also support recovery if given the chance. The Amazon stands at a crossroads, its future balanced between multiple possibilities. Which path we take, or rather, which path we're already on, will determine whether the world's largest rainforest persists or transforms into something fundamentally different. The choice is being made now, through thousands of decisions about land use, economics, conservation. The forest watches, patient and precarious, waiting to see what we decide. Future space missions might use solar sails, enormous reflective sheets pushed by sunlight, to reach nearby star systems over centuries. Light has no mass, but it carries momentum. When photons from the sun hit a reflective surface, they transfer that momentum, creating pressure. It's incredibly tiny. Sunlight at Earth's distance exerts about 9 micronewtons of force per square meter. But in the vacuum of space, with no friction to slow you down, even tiny forces accumulate over time. A solar sail would be an enormous sheet of reflective material, perhaps kilometers across, but only micrometers thick. Sunlight hitting it would provide continuous acceleration, gentle but relentless. Unlike rockets, which burn through fuel and then coast, a solar sail would accelerate as long as it remained in sunlight. Near the sun, the push would be stronger. A spacecraft could dive close to the sun, closer than Mercury, where the light is intense, gaining maximum acceleration before heading outward. Over months and years, it would build up speed. Over decades, it might reach a significant fraction of light speed, perhaps 10% or 20%. At those velocities, the nearest star systems become reachable, though reachable still means centuries of travel. A solar sail traveling at 10% of light speed would take about 40 years to reach Alpha Centauri. The people who launched it would likely be dead before it arrived, but it would arrive carrying instruments or perhaps even preserved biological samples, an emissary from humanity to other star systems. Japan's Ikaros mission demonstrated solar sailing in 2010, successfully using sunlight for propulsion. It proved the concept works, even if the scale was tiny compared to what an interstellar mission would require. The technology is patient. Solar sails don't need fuel, just sunlight and time. They embody a different philosophy of space exploration, not fast, heroic journeys, but slow, patient ones. Spacecraft that accelerate for decades or centuries, eventually reaching destinations that chemical rockets could never approach. In the deep future, solar sails might carry humanity's messages, and perhaps eventually humanity itself, to other stars. Not quickly, but inevitably pushed by starlight across the vast darkness between suns. In about 10,000 years, the constellations will look noticeably different as stars drift in their individual orbits around the galaxy. We think of constellations as eternal: Orion the Hunter, Ursa Major the Great Bear, patterns humans have recognized for thousands of years. But the stars in these constellations aren't actually related to each other. They just happen to lie in roughly the same direction from Earth, like buildings on different streets that appear aligned when viewed from one specific corner. And they're all moving. Each star orbits the galactic center at its own velocity, following its own path. The Sun moves at about 230 kilometers per second relative to the galaxy's center. Other stars move at different speeds in different directions. Slowly, over thousands of years, these different motions change the apparent positions of stars as seen from Earth. In 10,000 years, the Big Dipper will be noticeably distorted. The handle will stretch and curve differently. Orion's belt will tilt. The familiar patterns will warp into unfamiliar shapes. In 50,000 years, most constellations will be unrecognizable. The stars we see as patterns today will have drifted apart or realigned into new configurations. Future humans, if there are future humans, might look up and see entirely different patterns, create entirely different mythologies to explain them. Even our fixed reference points are temporary. The North Star slowly changes due to Earth's precession. The constellations gradually morph. The galaxy rotates, carrying everything with it in a slow cosmic waltz. There's something both unsettling and beautiful about this. The patterns we've used for navigation, for marking seasons, for telling stories, they're all temporary. The stars we see as eternally grouped together are just passing ships in the night, briefly aligned before continuing on their separate journeys. But for now, for this brief window of cosmic time, Orion still hunts across the winter sky. The Big Dipper still points to north. The patterns hold, patient and familiar, waiting for the slow drift of stellar motion to eventually reshape them into something new. By the 2100s, we may have molecular assemblers that build objects atom by atom, manufacturing anything from food to electronics. Imagine a device that could arrange atoms with precision, placing them exactly where needed to build any structure you desired. Carbon atoms arranged one way make diamond. Arranged differently, they make graphite. With perfect control over atomic placement, you could build anything the laws of chemistry allow. This is the vision of molecular manufacturing, not building objects by cutting, shaping, and joining parts, but by assembling them atom by atom from the bottom up. It's the ultimate in precision manufacturing, limited only by available atoms and thermodynamic constraints. The concept has been around since the 1980s, popularized by Eric Drexler's writings on nanotechnology. The basic physics seems sound. Atoms can be manipulated individually, as demonstrated by scanning tunneling microscopes that can move single atoms on surfaces. The question is whether the process can be scaled up and made practical. By the end of this century, we might have crude versions of this technology. Not Star Trek replicators that materialize Earl Grey tea from energy, but devices that can assemble complex molecules and structures with atomic precision. Medical nanomachines. Materials with impossible properties. Electronics built atom perfect. Food would still require biological molecules, but molecular assemblers could potentially arrange proteins, carbohydrates, and fats into nutritious forms, building synthetic steaks molecule by molecule. Electronics could be built with perfect precision, no manufacturing defects, no wasted material. The challenges are immense, controlling billions of atomic-scale operations simultaneously, managing the heat generated, preventing errors from accumulating, finding the right building blocks and reaction pathways. These aren't trivial problems, but the potential makes them worth pursuing. Manufacturing that produces exactly what's needed, nothing wasted, built atom perfect every time. It would be the ultimate expression of precision, the final evolution of human crafting ability, not shaping matter in bulk, but commanding it atom by atom. In 240 million years, our solar system will complete one full orbit around the Milky Way galaxy, a period called a cosmic year. Right now, you're moving through space faster than you probably realize. Earth orbits the Sun at about 30 kilometers per second, but the Sun itself is also moving, orbiting the center of the Milky Way galaxy at roughly 230 kilometers per second, carrying the entire solar system along with it. The Sun's orbit around the galaxy takes approximately 250 million years. This period is sometimes called a cosmic year or galactic year. In that time, we complete one full circuit around the galactic center, traveling through different regions of the galaxy, passing through spiral arms and quieter spaces between them. The last time we were at this position in our galactic orbit was about 240 million years ago, in the Triassic period. Dinosaurs hadn't evolved yet. Mammals were still in the future. Pangaea was intact. Life on Earth looked nothing like it does today. We've made roughly 20 orbits since Earth formed 4.6 billion years ago. We might make another 20 before the Sun exhausts its fuel and swells into a red giant. Each orbit takes us on a journey through different regions of the galaxy, exposing us to different radiation environments, different densities of stars and gas clouds. Some scientists speculate these galactic cycles might influence life on Earth. Passing through dense spiral arms might trigger cosmic ray bombardment that affects mutation rates, or encounter massive molecular clouds that disturb the Oort cloud and send comets cascading inward. The evidence is inconclusive but intriguing. What's certain is that we're on a journey far longer and stranger than most people realize. We orbit the Sun, yes, but the Sun orbits the galaxy, and the galaxy itself is moving through space. We're nested in orbits within orbits, each on its own timescale, each taking us places we've been before and will visit again, on schedules measured in hundreds of millions of years. The cosmic year ticks on, patient and vast, marking time on scales that make human history feel like a single breath. The Grand Canyon will continue eroding, and in about 6 million years, it might look completely different or even disappear entirely. The Grand Canyon is one of Earth's most iconic landscapes, a mile-deep gorge carved by the Colorado River over millions of years, exposing rock layers that span nearly 2 billion years of geological history. It feels permanent, eternal, as if it's always been there and always will be. But erosion never stops. Every rainstorm carries away tiny particles. The river continues cutting deeper, while the canyon walls gradually crumble and retreat. Freeze-thaw cycles crack rocks. Wind abrades surfaces. Gravity pulls weakened material downward. The canyon is relatively young. Most of it was carved in the last 5 to 6 million years, though the river itself might be older, following earlier paths. And it won't last forever. In another 6 million years, the canyon might be unrecognizable, perhaps much wider and shallower, perhaps filled with sediment from upstream erosion, perhaps bypassed entirely if the river finds a new course. Mountains rise and fall, canyons form and disappear. The landscape is constantly reshaping itself, just so slowly that we perceive it as static. But it's not. It's flowing, changing, responding to gravity and water and weather with the same inevitability that rivers flow downhill. There's something melancholic about impermanence on geological scales. The Grand Canyon has inspired millions of visitors, featured in countless photographs and paintings, served as a natural laboratory for understanding Earth's history. But it's temporary, spectacular, yes, but just a brief moment in the landscape's eternal transformation. Yet this impermanence is also what makes it precious. The canyon exists now because the conditions that created it happened to align. In a few million years, those conditions will change, and the canyon will transform into something else. We're fortunate to live during this particular moment of geological time, when this particular arrangement of rock and river creates this particular wonder. Everything flows. Everything changes. Even the most solid-seeming features of Earth's surface are just temporary sculptures, shaped by patient forces that never rest. Earth's day is gradually lengthening by about 1.7 milliseconds per century as the moon slowly drifts away from us. The moon is leaving, not dramatically, just about 3.8 centimeters per year. Roughly the rate fingernails grow, but it's leaving nonetheless. Pushed outward by tidal forces that transfer angular momentum from Earth's rotation to the moon's orbit. As the moon drifts away, Earth's rotation slows. The two are connected through tidal interactions. The moon's gravity raises tidal bulges on Earth, and friction from those bulges acts like a brake on Earth's rotation, while simultaneously pushing the moon to a higher orbit. The effect is tiny. Earth's day lengthens by about 1.7 milliseconds per century. You'd never notice in a lifetime, but over millions of years, it accumulates. Fossil evidence suggests that 400 million years ago, a year contained about 400 days, each about 22 hours long. The moon was closer, looming larger in the sky. In the far future, if Earth and the moon survive long enough, they'll reach a stable configuration where Earth's rotation period matches the moon's orbital period. probably about 47 current days long. At that point, Earth would always show the same face to the Moon, just as the Moon already shows the same face to Earth. But that won't happen for billions of years, and by then, the Sun will have other plans for the inner solar system. The Earth-Moon system won't have time to reach equilibrium before the Sun swells into a red giant. Still, the slow drift continues. Each month, the Moon is a little farther away. Each day, Earth's rotation is a tiny bit slower. The dance gradually winds down, energy dissipating into heat through tidal friction, until eventually the two bodies lock into their final, stable embrace. For now, the Moon still creates tides, still lights our nights, still helps stabilize Earth's axial tilt, but it's slowly, gently pulling away, receding into a higher orbit while Earth's days grow incrementally longer. The Sun grows approximately 10% brighter every billion years, meaning Earth will become uninhabitable to life as we know it in about 1 to 2 billion years. The Sun is getting brighter, not in a way you'd notice. The change is roughly 1% per 100 million years, but it accumulates. A billion years ago, the Sun was about 10% dimmer than today. A billion years from now, it will be 10% brighter. This happens because the Sun is gradually accumulating helium ash in its core. As hydrogen fuses into helium, the helium doesn't participate in fusion reactions. It just sits there, inert and dense. The core slowly contracts under the weight of this helium, which increases the pressure and temperature, which increases the fusion rate, which increases the Sun's energy output. For now, this is fine. Earth's climate has compensated through various feedback mechanisms. When the Sun was dimmer early in Earth's history, greenhouse gases were more abundant, keeping the planet warm enough for liquid water. As the Sun brightened, those gases decreased, maintaining habitability. But this compensation won't work forever. In about 1 to 2 billion years, the Sun will be bright enough that Earth's oceans begin evaporating faster than they can be replenished. Water vapor is a greenhouse gas, so more evaporation means more warming, which means more evaporation. A runaway greenhouse effect. Eventually, Earth will lose its oceans entirely. The atmosphere will become thick and hot, like Venus, but worse. Surface temperatures might reach hundreds of degrees. Complex life will become impossible long before that, perhaps in as little as 500 million years, though estimates vary. This isn't the Sun dying. That won't happen for another 5 billion years. This is just the Sun doing what hydrogen-burning stars do, gradually brightening as their cores evolve. It's normal stellar behavior, playing out on billion-year timescales. Life on Earth has perhaps another billion years, give or take. That's a staggeringly long time. Life has only existed for about 3.8 billion years total, so there's still about a quarter of Earth's habitable lifetime remaining. But it's not infinite. The clock is ticking, slowly but inexorably, powered by nuclear fusion in the Sun's core. The Andromeda Galaxy is approaching us at 110 kilometers per second and will collide with the Milky Way in about 4.5 billion years. Look up on a dark autumn night, away from city lights, and you might see a faint smudge near the constellation Andromeda. That's not a star, it's a galaxy, similar in size to our Milky Way, containing hundreds of billions of stars. And it's heading toward us. Andromeda is approaching at about 110 kilometers per second. In 4.5 billion years or so, the two galaxies will collide. Not violently, galaxies are mostly empty space, and stars are so far apart that actual collisions between them are unlikely. But gravitationally, it will be dramatic. The two galaxies will interpenetrate, their stars passing through each other like two swarms of bees merging. The combined gravitational field will disturb stellar orbits, sending some stars into new trajectories, ejecting others into intergalactic space. Gas clouds will collide, triggering waves of star formation. The supermassive black holes at each galaxy's center will eventually spiral together and merge. Over hundreds of millions of years, the galaxies will swing through each other, separate, then fall back together again, each passage mixing them further. Eventually, they'll settle into a single large elliptical galaxy, no longer the graceful spirals we see today, but a more uniform, oval distribution of stars. If Earth still exists then, a big if, given the sun's evolution, the night sky will be spectacular. For a period during the collision, the sky will be ablaze with stars from both galaxies, far more than we see today. New stars will be forming at prodigious rates. The galactic center might glow brilliantly. But it's so far in the future that it barely matters to anything recognizable as human civilization. 4.5 billion years is almost as long as Earth has existed. Life might have evolved into forms we couldn't imagine, or be extinct, or spread across the galaxy. By the time this collision happens, everything about Earth and its biosphere will likely have changed beyond recognition. Still, the galaxies fall toward each other, patient and inexorable, following the gravity that has been pulling them together for billions of years. In 5 to 7 billion years, the sun will expand into a red giant, potentially engulfing Mercury, Venus, and possibly Earth. Every star has a lifespan written in its mass. The sun, being medium-sized, will burn hydrogen in its core for about 10 billion years total. We're roughly halfway through that period now. The sun is middle-aged, stable, uneventful. But when the hydrogen runs out, things change. The core will contract, heating up until it's hot enough to fuse helium. Meanwhile, hydrogen fusion will continue in a shell around the core. The energy from this shell burning will push the sun's outer layers outward, swelling the sun into a red giant, perhaps 250 times its current diameter. Mercury will almost certainly be engulfed. Venus probably will be. Earth's fate is uncertain. The sun will lose mass as it expands, which will cause Earth's orbit to drift outward. Whether that drift is enough to save us from being consumed depends on details we can't predict perfectly. But even if Earth escapes being engulfed, it won't be spared. The sun's increased luminosity will boil away our oceans long before the red giant phase begins. The atmosphere will be stripped away. The surface will be scorched to bare rock, then melted. Earth might survive as a charred, airless cinder orbiting a bloated red sun, or it might spiral inward and vaporize. This is billions of years away, so far in the future that the sun's death is essentially someone else's problem. If humanity survives even 1 million years, we'll likely have spread far beyond Earth. The loss of our homeworld, while symbolically profound, might be practically irrelevant to whatever we've become. The sun will eventually shed its outer layers, creating a planetary nebula, a beautiful shell of glowing gas expanding into space. The core will cool into a white dwarf, Earth-sized but tremendously dense. gradually radiating away its remaining heat over trillions of years. But that's the far future. For now, the sun burns steady and reliable, converting 4 million tons of mass into energy every second, giving us light and warmth and the conditions for life. Enjoy it while it lasts. Future intelligent machines might outlast biological life by billions of years, becoming the primary torchbearers of consciousness. Life as we know it has constraints. We need specific temperature ranges. Too cold and chemistry stops, too hot and molecules break down. We need protection from radiation. We need energy sources we can metabolize. We're fragile in countless ways, adapted to Earth's conditions but poorly suited for most of the universe. Machine intelligence wouldn't face the same limitations. A computer doesn't need oxygen or water. It can operate in hard vacuum, in extreme cold, potentially even in high radiation environments with proper shielding. Where biological life struggles, machines might thrive. If we create truly intelligent machines, artificial minds with genuine consciousness, subjective experience, the capacity for thought and feeling, they might be our longest-lasting legacy. Long after biological humans are extinct or evolved into something unrecognizable, machine intelligences might persist. They could witness the sun's death, having long since migrated to other star systems. They could watch galaxies collide over billions of years. They could potentially survive until the last stars burn out, billions of trillions of years from now, powered by increasingly exotic energy sources, black hole evaporation, perhaps, or mechanisms we haven't imagined yet. This raises profound questions. Would machine consciousness be real in the same way biological consciousness is? Would these artificial minds be our children, carrying forward something essential about humanity? Or would they be something else entirely, a different kind of consciousness that happens to have originated from our technology? We don't know. We can't know until we create them, if we ever do. But if consciousness can exist in substrates other than biological neurons, if mind is a pattern that can be implemented in silicon or optical circuits or quantum computers, then machine minds might outlast biological ones by incomprehensible time spans. They would be the witnesses to the universe's far future, watching entropy gradually win, stars die, galaxies disperse. They would carry the torch of awareness through the long, slow fade of the cosmos. Whether that counts as humanity's survival or our replacement is a question each person must answer for themselves. The last natural total solar eclipse on Earth will occur in about 600 million years, as the moon drifts too far away to cover the sun. There's a cosmic coincidence happening right now, a perfect alignment that won't last. The sun is about 400 times wider than the moon, but it's also about 400 times farther away. This makes them appear almost exactly the same size in our sky, a coincidence that allows total solar eclipses to occur. But this coincidence is temporary. As the moon drifts away from Earth, it appears smaller in the sky. Eventually, in roughly 600 million years, it will be far enough away that it can no longer completely cover the sun's disk. Eclipses will still occur, but they'll all be annular, with a ring of sunlight visible around the moon's silhouette. Total eclipses, where the moon perfectly covers the sun and reveals the corona, will be gone. We live in a privileged time. For most of Earth's history, the moon was closer, appearing larger. Total eclipses more common and longer lasting, In the far future, total eclipses won't happen at all. We exist in a sweet spot, a brief window of cosmic time when the moon and sun appear nearly identical in size. This window has been open for perhaps a few 100 million years and will remain open for another 600 million or so. In the grand sweep of Earth's 4.6 billion year history, that's about 20% of the total, a substantial fraction, but still finite. Ancient creatures witnessed total eclipses when the moon loomed larger, and eclipses lasted longer. Future creatures, if there are any, if life survives the sun's gradual brightening, will never see totality, only annular eclipses where a ring of fire remains visible. We're here during the eclipse sweet spot, the era when moon and sun match sizes with almost eerie precision. Every total eclipse is part of a finite set, a limited collection of events that will eventually run out. The moon drifts, the coincidence fades, and eventually the age of total solar eclipses ends, leaving only the memory of when two celestial objects happen to align just right. In 100,000 years, the Great Pyramid of Giza will likely have eroded significantly, though its foundations may persist for millions of years. The Great Pyramid of Giza has stood for about 4,600 years. It was ancient when Rome was founded, already weathered when Christ walked in Galilee. For most of human civilization, it has been there, a testament to human ambition and engineering, a monument that has outlasted empires. But it won't last forever. Wind and sand erode stone, rain dissolves limestone, temperature changes crack surfaces. The pyramid is being worn away, grain by grain, century by century. In another 100,000 years, the smooth casing stones that once covered the pyramid, most already stripped away, will be completely gone. The core blocks will be significantly weathered. The shape might remain recognizable but softened, rounded, more like a natural hill than a geometric structure. Yet the foundations, the deepest parts, could persist far longer. Stone buried underground erodes much more slowly than exposed surfaces. The bedrock the pyramid sits on isn't going anywhere. Future geologists, millions of years hence, might still detect anomalies in the rock, regular patterns, worked stone, evidence that something artificial once stood here. The same is true of most human structures. Our cities will erode, our buildings will collapse, glass will shatter and weather away, metal will corrode, concrete will crack and crumble. In 10,000 years, most traces of our civilization will be subtle, alterations to drainage patterns, deposits of non-natural materials, geological anomalies that suggest intelligent activity. But some foundations will persist, deep tunnels, carved bedrock, the deepest parts of our largest structures. These might remain detectable for millions of years, puzzles for whatever future investigators might find them. The pyramid is among the most durable things humans have built, and it's still temporary. Everything we create is temporary. The only question is how long temporary lasts. Decades, centuries, millennia, millions of years. But eventually, patient erosion wins. The wind and rain and time itself wear everything down to dust. The universe's cosmic microwave background radiation will become undetectable in about 1 trillion years as space expands and it redshifts beyond measurement. Shortly after the Big Bang, the universe was hot and dense, a plasma of particles and radiation. As it expanded and cooled, electrons and protons combined into hydrogen atoms, and suddenly radiation could travel freely. This first light has been traveling through space ever since, gradually cooling as space expands. Today we detect it as the cosmic microwave background, radiation at about 2.7 degrees above absolute zero, arriving from every direction, a faint echo of the universe's birth. It's one of our most important pieces of evidence for the Big Bang, a direct observation of the universe when it was only 380,000 years old. But space continues expanding. As it does, this radiation stretches, redshifting to longer and longer wavelengths, becoming fainter and cooler. Eventually, in about 1 trillion years, it will have redshifted so far that it becomes undetectable. The wavelengths too long, the energy too low, the signal lost in background noise. Future civilizations that arise after this point won't be able to see the cosmic microwave background. One of our best pieces of evidence for the universe's origin will be gone, invisible, beyond their technological reach, no matter how sophisticated their instruments. They'll have to infer the Big Bang from other evidence. The abundance of light elements, the expansion of space itself, mathematical models, and indirect observations. But they won't have our view, won't be able to see the universe's baby picture the way we can. We live in a time when the universe reveals its history relatively clearly. We can see the cosmic microwave background, observe distant galaxies showing us the universe's youth, measure the expansion with precision. This window is temporary. We're fortunate to exist during an era when the evidence remains accessible. Eventually, that window closes, the evidence fades, and the universe becomes more mysterious again, its origins harder to discern, its early history hidden behind the veil of cosmic expansion. In roughly 1 trillion years, galaxies outside our local group will have redshifted beyond visibility, making the universe appear empty to distant observers. The universe is expanding, and that expansion is accelerating. Distant galaxies are receding from us faster and faster, driven by dark energy, a mysterious force that pushes space itself outward. Currently, we can see thousands of galaxies, spanning billions of light years. Our telescopes reveal a rich cosmos, filled with stellar cities scattered across the void. But as expansion accelerates, these galaxies recede faster, their light increasingly redshifted. Eventually, galaxies beyond our local group, the small cluster including the Milky Way, Andromeda, and a few dozen smaller galaxies bound together by gravity, will redshift beyond visibility. Their light will stretch to such long wavelengths that it becomes undetectable, not because the galaxies cease to exist, but because space between us and them expands faster than light can cross it. In about 1 trillion years, an astronomer in our galaxy would look out and see almost nothing, just our local group of gravitationally bound galaxies. Beyond that, darkness, empty space stretching to infinity, with no visible galaxies, no distant light, nothing to suggest a larger universe exists. They would be cosmologically isolated, trapped in a small island universe with no evidence of anything beyond. They might develop theories, mathematical models, suggesting a larger cosmos, but they'd have no direct observations to confirm it. The universe would appear to be just our local group, surrounded by infinite empty darkness. We're fortunate to live when we do, when the universe still reveals itself, when we can see deep into space and deep into time, when the evidence of cosmic history remains accessible. This window is temporary, already closing, slowly but inexorably, as expansion accelerates and distant light fades. Future civilizations might look at our observations with envy, seeing a richness of cosmic structure they can no longer access. We witness a universe they'll only be able to imagine. The last star in the universe will burn out in approximately 100 trillion years, ending the stelliferous era of cosmic history. Stars can't burn forever. They're powered by nuclear fusion, and fusion requires fuel. Hydrogen to fuse into helium, helium to fuse into heavier elements for more massive stars. Eventually, the fuel runs out. Small stars burn slowly, conserving their hydrogen over immense timescales. The smallest red dwarfs might burn for 10 trillion years or more, 1,000 times longer than the current age of the universe. But even they will eventually exhaust their fuel. Around 100 trillion years from now, the last star will flicker out. The stelliferous era, the age of stars, will end. The universe will enter the degenerate era, lit only by the fading glow of white dwarfs and brown dwarfs too small to have ever ignited fusion. It won't be sudden. Stars will become rarer over time, the galaxy gradually darkening. Eventually, you could travel for light years without encountering a shining star. The night sky, if there were anyone to observe it, would be profoundly dark, just the faint infrared glow of cooling stellar remnants. This isn't death exactly. The universe will continue. Black holes will persist, slowly evaporating through Hawking radiation. Occasional collisions between stellar remnants might create brief flashes. Protons might decay, if theories about their instability are correct, releasing small amounts of energy over incomprehensible timescales. But the age of stars, our age when the universe is bright and dynamic and stars illuminate the darkness, will be over. We live in the universe's youth, when star formation is still active, when galaxies shine, when the cosmos is energetic and bright. 100 trillion years seems infinite, but it's not. It's just very, very long. The stars will go out one by one as fusion runs its course and gravity settles into its final configurations. The universe will grow dark and cold, entering a new era where different processes dominate, where the brilliance of stars becomes a distant memory encoded in cooling stellar remnants. By 1040 years from now, even the most stable atomic nuclei will have decayed. Assuming proton decay theories are correct, matter feels permanent. An atom of iron is an atom of iron, stable, unchanging, eternal. Most atomic nuclei don't decay. They just persist indefinitely, at least according to observations over human timescales. But some theories predict that even protons, the building blocks of atomic nuclei, are ultimately unstable. They might decay with extraordinarily long half-lives, perhaps 1034 years or longer. We've never observed proton decay. If it happens, it's so rare that we can't yet detect it. But given enough time, truly staggering amounts of time, proton decay might dismantle all ordinary matter. By 1040 years or so, if these theories are correct, even the most stable nuclei will have decayed. Every atom would have broken down into lighter particles, positrons, neutrinos, photons. Matter itself would be temporary, just taking an extraordinarily long time to reveal its impermanence. Everything solid, rocks, planets, stellar remnants, would eventually evaporate away, leaving only elementary particles and radiation. This timescale is beyond comprehension. 1040 years is to the current age of the universe what the age of the universe is to a single second, and then some. It's so long that calling it the far future feels inadequate. At these timescales, we're not even sure the laws of physics remain constant. Quantum fluctuations might create random structures. Space itself might undergo phase transitions. The universe becomes so strange that our current physics might not apply. But if proton decay is real, then matter, the stuff everything is made of, is just a temporary arrangement, stable on human timescales and even astronomical timescales, but ultimately subject to the same entropy that governs everything else. Nothing lasts forever, not stars, not planets, not even atoms themselves. The universe marches toward maximum entropy, slowly dismantling every structure, converting everything into its simplest forms, and even matter might not survive the journey to the end. In 100 years, the universe might experience heat death, a state of maximum entropy where no energy remains available for work. Entropy always increases. This is the second law of thermodynamics, one of the most fundamental principles in physics. Every process, every interaction, every change increases the universe's total entropy, its degree of disorder, its unavailability of energy for doing work. Eventually, entropy reaches a maximum. All energy becomes evenly distributed. Thermal equilibrium extends across all space, and nothing can happen anymore because there are no energy gradients left to drive processes. This is heat death, not hot but cold, everything cooled to the same uniform temperature, just barely above absolute zero. By 100 years or so, a Google years, the universe might reach this state. All stars will have burned out. All black holes will have evaporated. All matter will have decayed or been consumed. What's left will be a diffuse soup of elementary particles and radiation, spread thin across an expanding void, everything at the same temperature, nothing happening anymore. Not darkness, because darkness implies the possibility of light. Not silence, because silence implies the possibility of sound. Just equilibrium. A universe where nothing changes because there's no energy difference anywhere to drive change. It's a cold, quiet ending. No dramatic collapse, no final explosion, just gradual winding down, heat spreading out, energy becoming unavailable, until finally everything stops. Some theories suggest this might not be the absolute end. Quantum fluctuations might occasionally create brief, random events, even in a heat-dead universe. But these would be rare beyond imagination, separated by timescales that make a Google years seem brief. We're so far from heat death that it barely matters. The universe is young, vibrant, full of stars and energy and change. Heat death is so distant that whether it even happens depends on physics we don't fully understand yet. But if entropy always increases, if the second law holds forever, then eventually, inevitably, everything runs down. Some theories suggest the universe could experience false vacuum decay at any moment, where all physics suddenly changes throughout space. Our universe might be metastable, stable for now, but not in its lowest energy state, like a ball balanced on a hill instead of resting in a valley. The current configuration of quantum fields might not be the most stable possible arrangement. If that's true, quantum tunneling could trigger a transition to the true vacuum state. This would create a bubble of space with different physical laws, different particle masses, different force strengths, possibly different fundamental constants. This bubble would expand at the speed of light, converting everything it touched. We would have no warning. The bubble's edge moves at light speed, so we wouldn't see it coming. It would simply arrive instantly and completely, rewriting the laws of physics as it passed. Atoms might disintegrate. Chemical bonds might become impossible. The universe as we know it would cease to exist, replaced by something governed by different rules. This is purely theoretical. We have no evidence that our vacuum is false, or that such a transition is possible. But we can't rule it out either. The universe might be sitting in a metastable state, waiting for a quantum fluctuation to trigger collapse. If it happened, it would be the most complete and sudden ending imaginable. Not gradual heat death or stellar burnout, but instant transformation. Everything changed in an instant, spreading outward at light speed, erasing the current universe, and replacing it with something utterly different. The good news, if there is good news, is that we wouldn't suffer. We wouldn't see it coming. One moment, the universe exists with its current laws. The next moment, those laws are different, and we're something else, or nothing at all. It probably won't happen, but the fact that it could, that the universe might be balanced on a knife edge between stability and transformation, adds a certain uncertain tension to existence. We live in what might be borrowed time, in laws of physics that might not be permanent. Black holes will dominate the extremely distant future, slowly evaporating through Hawking radiation over Google-scale time spans. After the last star dies, after ordinary matter decays, black holes will be the most substantial objects remaining in the universe. They'll persist for incomprehensible spans of time, gradually evaporating through a process Stephen Hawking discovered in the 1970s. Hawking radiation occurs at the event horizon, where quantum fluctuations create particle-antiparticle pairs. Normally, these pairs annihilate immediately, but at a black hole's edge, one particle can fall in while the other escapes, carrying away a tiny amount of the black hole's mass energy. The process is extraordinarily slow. A solar mass black hole would take about 1067 years to evaporate completely. Supermassive black holes, millions or billions of solar masses, would take vastly longer, perhaps 10–100 years. During evaporation, black holes emit primarily photons and light particles, gradually losing mass. As they shrink, they get hotter and radiate faster. The final moments would be dramatic, a burst of radiation as the last of the mass evaporates. But those final moments might not arrive until 10–100 years from now. So black holes become the universe's longest-lasting structures. Long after stars, planets, and atoms have disappeared, black holes will remain, patient and dark, slowly bleeding away their mass through quantum processes. Eventually, even they will be gone. The last black hole will evaporate, releasing its final burst of radiation into the void. And then, nothing substantial remains. Just photons and light particles spreading through ever-expanding space, growing cooler and more diffuse, approaching but never quite reaching absolute zero. Black holes represent a kind of temporal refuge, places where information and energy remain concentrated while the rest of the universe dissipates. But even this refuge is temporary. Hawking radiation ensures that nothing lasts forever. The universe marches toward maximum entropy, and even black holes must eventually surrender to the inexorable logic of thermodynamics. They're the last holdouts, the final concentrations of matter energy in a universe growing cold and empty. But their time is finite too, just measured in timescales so vast they defy comprehension. In the incomprehensibly distant future, quantum fluctuations might spontaneously create Boltzmann brains, conscious observers that pop into existence randomly. Given infinite time, anything permitted by quantum mechanics will eventually happen through random fluctuations. Particles will occasionally arrange themselves into complex structures just by chance. Usually these arrangements are simple, a few atoms clustering together. But very rarely, fluctuations might create something more complex. A Boltzmann brain is a hypothetical self-aware entity that forms spontaneously from random fluctuations. It would be a brain, complete with memories, thoughts, subjective experiences, that pops into existence fully formed, exists for a moment, then dissipates. This sounds absurd, but the mathematics is troubling. In an infinite or sufficiently long-lived universe, random fluctuations that create a conscious observer are more probable than the entire ordered history that led to observers like us. It's statistically more likely to fluctuate into existence as a disembodied brain with false memories than to evolve through billions of years of cosmic and biological history. This is called the Boltzmann brain problem, and it challenges our understanding of cosmology. If most conscious observers in the universe's history are random fluctuations rather than evolved beings, then our own experiences, which seem to indicate an ordered universe with a consistent past, are probably illusions, false memories created by chance. Most physicists think this indicates something wrong with our cosmological models, rather than suggesting we're actually Boltzmann brains. But in the deep future, in a heat-dead universe where nothing happens for Google-scale timescales, occasional quantum fluctuations creating brief moments of consciousness might be the only events that occur. Imagine, in 100 years, a random fluctuation creates a brain that exists for a fraction of a second, experiences a thought, then dissipates. Then nothing for another incomprehensible span until another fluctuation. Another brief moment of awareness. It's a strange and melancholic vision of the far future. Consciousness reduced to random sparks in an otherwise dead universe. Brief candles of awareness flickering in eternal darkness. The cosmic calendar that compresses all of history into 1 year will need updating. The first stars formed earlier in the year than we once thought. Carl Sagan popularized the cosmic calendar, a way to visualize the universe's 13.8 billion year history compressed into a single year. The Big Bang happens at midnight on January 1st, and the present moment is midnight on December 31st. All of human history occurs in the final seconds before midnight. But our understanding keeps changing. The James Webb Space Telescope has found galaxies that formed earlier than we expected, perhaps only 200 to 300 million years after the Big Bang. These observations push back the date when the first stars ignited, when the first galaxies assembled. On the cosmic calendar, this means adjusting dates by perhaps a day or two, galaxies forming in mid-January rather than late January. It seems minor, but it represents a significant shift in our understanding of how quickly structure formed after the Big Bang. Every new observation refines our cosmic timeline. We discover that planets formed earlier than we thought, that life on Earth appeared sooner after the planet cooled, that complex cells evolved faster than we expected. The calendar constantly needs updating as we learn more. This is how science works, not discovering fixed truth, but continuously refining our understanding. The broad outline remains stable: Big Bang, cosmic expansion, star formation, galaxy evolution, solar system formation, life on Earth, but the details shift as observations improve. In a sense, we're still writing the universe's history book. We know the major chapters, but we're constantly revising the specifics, discovering that events happened at different times than we first believed. The cosmic calendar will continue evolving as our telescopes improve, as we gather more data, as theoretical models become more sophisticated. What we teach as the universe's timeline today will be slightly different from what we teach a decade from now. Not wrong exactly, just incomplete, awaiting refinement. The universe reveals itself gradually, and we're patient scribes, recording what we learn, updating our timelines, getting incrementally closer to understanding when and how everything happened. By the time the sun becomes a white dwarf, it will have lost about half its current mass, leaving the outer planets in wider orbits. When the sun exhausts its hydrogen fuel and swells into a red giant, it won't just expand, it will also shed mass. The outer layers will be blown away in a stellar wind, gradually escaping into space. Eventually, the sun will eject perhaps 50% of its current mass, leaving behind a dense white dwarf core. This mass loss has consequences for the planets. Orbital dynamics depend on the central star's mass. The less massive the star, the weaker its gravitational pull, the wider the orbits. As the sun loses mass, the planets will drift outward to new orbits. Jupiter, currently orbiting at about 5 astronomical units, might drift out to 7 or 8 AU. Saturn would move proportionally farther. The outer planets would spread out, their years lengthening as their orbits expand. But they'd still be there, still orbiting the white dwarf remnant, still following the same basic patterns, just in a cooler, quieter solar system. The white dwarf sun would be Earth-sized, but tremendously dense, gradually radiating away its heat, providing little warmth to its remaining planets. Mercury and Venus will likely be gone, consumed during the red giant phase. Earth's fate is uncertain, possibly engulfed, possibly surviving as a scorched remnant. But the outer giants should persist, patient and cold, circling a dying star. Over trillions of years, the white dwarf will cool, fading through yellow, red, brown, eventually becoming a black dwarf, a stellar remnant so cool it emits virtually no light. The planets will still orbit this dark cinder, following their eternal paths around a sun that no longer shines. It's a melancholic vision, a solar system that survives its star's death, but is transformed into something cold and dark, planets circling endlessly in the darkness, carrying no life, serving no purpose, just following orbital mechanics until what? Until gravitational interactions eventually eject them? Until the protons in their atoms decay? Until the end of time itself. Future cosmic civilizations might witness stars being ejected from galaxies at near light speeds during galactic collisions. When galaxies collide, their gravitational fields create chaos. Most stars don't actually collide. Space is so vast that stellar impacts are unlikely. But orbits become scrambled. Stars that were peacefully circling their galaxy's center suddenly find themselves flung onto new trajectories. Some stars get ejected entirely, gravitational slingshots that launch them out of the galaxy at tremendous speeds. These hypervelocity stars can reach velocities of 1,000 kilometers per second or more, not quite light speed, but fast enough to escape the galaxy's gravity permanently. Once ejected, these stars become intergalactic wanderers. They leave their home galaxy behind and drift through the void between galaxies, orphaned by gravitational chaos. If they have planets, those planets come along for the ride, suddenly finding themselves in intergalactic space, their sky dominated not by the Milky Way, but by distant galactic smudges billions of light years away. We've already detected some hypervelocity stars in our galaxy, likely ejected by close encounters with the supermassive black hole at the galactic center, or by past galactic interactions. They're racing toward the edge of the Milky Way at speeds that will carry them into intergalactic space. Future civilizations might witness this on grand scales. When the Milky Way and Andromeda collide in 4.5 billion years, millions of stars might be ejected in the chaos. Imagine watching your sun being flung out of the galaxy, the Milky Way receding behind you as you're launched into the cosmic void, spending eternity alone in the darkness between galaxies. It wouldn't be violent. The acceleration would be gradual, barely perceptible. But it would be permanent. Your star would leave behind everything it knew, joining the lonely population of intergalactic stars, orphans of galactic collisions, wandering the void forever. These stars would see the universe differently, not from within a galaxy's comforting light, but from the lonely darkness between them, surrounded by distant galactic islands, forever traveling, forever alone. In 1 million years, human faces may look quite different due to continued evolution, potentially with larger eyes adapted for screen viewing. Evolution hasn't stopped. We sometimes think of humans as finished products, but evolution continues as long as there's variation, selection, and reproduction. The question is whether modern technology and medicine have changed the selective pressures enough to alter our evolutionary trajectory. Some researchers speculate about future human appearance based on current trends. If we spend increasing time indoors looking at screens, might we evolve larger eyes to capture more light? If our diets remain soft and processed, might our jaws become smaller and teeth fewer? If we rely on technology for temperature control, might we lose body hair? These are speculations, not predictions. Evolution doesn't have goals or direction. It responds to whatever selective pressures exist. And in modern humans, those pressures are heavily modified by culture, technology, and medicine. We can survive conditions our ancestors couldn't. We reproduce across genetic lines our ancestors kept separate. Sexual selection operates differently when mate choice is influenced by cultural values rather than just survival fitness. 1 million years is long enough for significant change. Modern humans emerged from earlier hominids over roughly that time frame, but the direction of change depends entirely on what traits are selected for, and that depends on how our civilization and environment evolve. We might engineer ourselves deliberately through genetic modification long before natural selection has time to work. We might merge with technology, making biological evolution irrelevant. We might go extinct, or we might split into multiple varieties adapted to different environments: Earth, Mars, orbital habitats, each with different selective pressures. The human face of the far future might look different, but not necessarily because of screen time, more likely because we've deliberately modified ourselves, or adapted to life off Earth, or evolved in directions we can't currently predict. Evolution continues, but in a species that's partially taken control of its own evolution, the path forward is radically uncertain. The continents will continue their waltz across Earth's surface, creating and destroying ocean basins in cycles lasting hundreds of millions of years. Right now, the Atlantic Ocean is growing while the Pacific shrinks. In about 250 million years, they might reverse, the Atlantic beginning to close as the Americas drift back toward Europe and Africa, while new oceans open elsewhere. This is the supercontinent cycle, first recognized by geologist J. Tuzo Wilson. Continents gather into supercontinents, which then break apart, with the fragments dispersing across the globe before eventually gathering again. The cycle takes roughly 400 to 600 million years. Pangaea was the most recent supercontinent, assembled about 300 million years ago and beginning to break apart around 200 million years ago. We're currently in the dispersal phase, with continents spread around the globe. But they'll gather again. The driving force is mantle convection. Heat from Earth's core creates circulation in the semi-molten mantle, which drags the surface plates along. Where hot material rises, continents are pushed apart. Where cool material sinks, continents are pulled together. This process has been ongoing for billions of years and will continue until Earth's interior cools enough that the mantle stops convecting, probably several billion years from now, though the exact timing is uncertain. Future supercontinents are already being sketched out. Pangaea Ultima has the Americas colliding with Africa. Amasia has all continents gathering around the Arctic. Aurica has a different configuration entirely. Which actually happens depends on details of mantle convection we can't predict perfectly over such long time scales. But the broad pattern is clear: gather, disperse, gather again. Ocean basins open and close like doors. Mountain ranges rise and erode. Coastlines shift thousands of miles. Geography is fluid over geological time, the continents dancing their slow waltz across the planet's surface. Nothing about Earth's geography is permanent. Everything is temporary, just on time scales so long that individual human lives can't perceive the motion. But it's there, constant and inexorable, reshaping the planet continuously. In about 50 million years, Africa will collide with Europe, closing the Mediterranean Sea and creating a new mountain range. The Mediterranean Sea is dying. Not quickly. It's been around for millions of years and will persist for millions more. But it's doomed. Africa is drifting northward at a few centimeters per year, gradually closing the gap between it and Europe. In roughly 50 million years, the collision will be complete. Africa will crash into Europe, crumpling the seafloor between them upward into a new mountain range. The Mediterranean will be squeezed out of existence, its waters dispersed or trapped in inland seas. This has happened before. The Mediterranean has closed and reopened multiple times in Earth's history. About 5.3 million years ago, it was cut off from the Atlantic and largely dried up, the Messinian salinity crisis. When the barrier eventually broke, the Atlantic rushed back in, refilling the basin in what must have been one of the most spectacular floods in Earth's history. But the next closure will be more permanent. Africa and Europe will join, creating a mountain range that might rival the Himalayas. The Alps are a preview. They formed from earlier collisions between the African and European plates, and they're still rising as the collision continues. What's now Mediterranean seafloor will become mountain peaks. Fossils of sea creatures will be found at high elevations, as they are in the Himalayas, where marine fossils from the Tethys Sea are now at 20,000 feet elevation. For now, the Mediterranean persists, beautiful, historic, bordered by civilizations that have risen and fallen on its shores. But its time is limited. The plates continue their slow convergence. In 50 million years, tourists won't sail its waters. They'll climb mountains where those waters used to be, finding seashells embedded in rock thousands of feet above sea level. Evidence of an ocean that once separated continents, but was eventually crushed out of existence by their collision. Future Mars might be terraformed over thousands of years, potentially developing breathable atmosphere and liquid water oceans. Mars was once warmer and wetter. Ancient riverbeds scar its surface. Minerals requiring liquid water to form are common. Billions of years ago, Mars might have had oceans, rainfall, possibly even life, but it lost most of its atmosphere, cooled, dried out, becoming the frozen desert we see today. Could we reverse this? Terraforming Mars, transforming it into an Earth-like world, is theoretically possible but enormously difficult. We'd need to thicken the atmosphere, warm the planet, melt the ice, establish a water cycle. One approach: release Mars's trapped CO2. The polar ice caps contain frozen CO2. The soil might hold more. If we could warm Mars enough to sublimate this CO2 into the atmosphere, it would create greenhouse warming, which would release more CO2, creating a feedback loop. We might use orbital mirrors to focus sunlight on the poles, or impact asteroids to deliver heat and volatiles, or release greenhouse gases far more potent than CO2. Over centuries or millennia, Mars might warm enough for liquid water to exist on its surface. Next, we'd need oxygen. This might require biological approaches, hardy microorganisms engineered to photosynthesize in Martian conditions, gradually converting CO2 into oxygen over thousands of years. Eventually, breathable atmosphere. The time scale would be immense, not years, but millennia. Many generations would work on this project, none living to see completion. And there are profound ethical questions. Do we have the right to transform another planet? Should Mars be preserved as a pristine laboratory for studying planetary evolution? What obligations do we have to any potential Martian microbes? But if we choose to terraform, if we commit to the centuries-long project, Mars might one day have blue skies, rain, rivers, perhaps even grasslands and forests. A second Earth, built slowly and deliberately through the patient application of planetary engineering. Or we might decide preservation is more valuable than transformation. The choice, if we make it, will say much about what kind of species we've become. Earth's magnetic field reverses irregularly, with the next flip potentially beginning within the next few thousand years. Earth has a magnetic field generated by circulation in the molten iron core. This field protects us from solar radiation and cosmic rays, channeling charged particles toward the poles where they create auroras. It's been relatively stable throughout human history, pointing roughly north-south, but it flips. Every few 100,000 years on average, the magnetic field weakens, becomes chaotic, and reverses. North becomes south, south becomes north. The last reversal was about 780,000 years ago, which means we're arguably overdue for the next one, though the timing is highly irregular. The reversal doesn't happen instantly. The field gradually weakens over thousands of years, becomes disorganized with multiple poles, then reorganizes in the opposite direction. During the transition, the field is weaker and more complex. Not a simple north-south dipole, but a complicated multipolar arrangement. During this time, we'd be more exposed to solar radiation and cosmic rays. Satellites might be damaged more frequently. Auroras would appear at unusual latitudes, perhaps over the equator. Compasses would become unreliable as magnetic north wandered unpredictably. But it wouldn't be catastrophic. Life has survived many reversals. They're recorded in rocks where iron minerals align with the magnetic field of their time, creating a record of past pole positions. There's no evidence of mass extinctions associated with reversals. Still, for a technological civilization dependent on satellites and power grids, a prolonged period of weak, chaotic magnetic field could be challenging. We'd need to harden systems against increased radiation, develop navigation methods that don't rely on magnetic compasses. The field is currently weakening, about 9% weaker than 170 years ago. Some researchers think this might indicate a reversal beginning, though the evidence is ambiguous. It might just be normal variation. We won't know until it happens, or doesn't. Either way, the magnetic field will continue its irregular dance, flipping back and forth on time scales of hundreds of thousands of years, indifferent to whatever civilization might be affected. The last light from the cosmic microwave background will fade into undetectability in about 3 trillion years, erasing direct evidence of the Big Bang. The cosmic microwave background is our clearest window into the universe's birth. It's the afterglow of the Big Bang radiation that's been traveling through space for 13.8 billion years, gradually cooling as the universe expands. Today we detect it at about 2.7 degrees above absolute zero, a faint whisper from when the universe was 380,000 years old. But this whisper is fading. As space expands, the radiation stretches to longer wavelengths, becoming cooler and fainter. In about 3 trillion years, it will have redshifted so far that even the most sensitive instruments imaginable couldn't detect it. The wavelengths would be too long, the photon energies too low, the signal irretrievably lost in background noise. Future civilizations arising after this point would face a profound mystery. They'd have no direct observational evidence of the Big Bang. They could infer it from other clues: the expansion of space, the abundance of hydrogen and helium, mathematical models. But they wouldn't be able to see the cosmic microwave background, to measure its temperature fluctuations, to use it as we do to understand the universe's early conditions. They'd have to take the Big Bang on theoretical faith. supported by indirect evidence but lacking the direct observations we're fortunate enough to have. Their cosmology would be more difficult, more uncertain, built on inferences rather than measurements. We live during a privileged era, young enough that the evidence of the universe's origin remains accessible, yet old enough that stars and galaxies have formed, creating observers capable of understanding what they're seeing. This window is temporary. It opened billions of years ago when the first intelligent life appeared, and it will close trillions of years from now when the last traces of the Big Bang fade beyond detection. The universe gradually erases its own history, redshifting evidence into invisibility. We're here at the right time to read the story. Future observers won't be so fortunate. Gravitational waves will be the only way future civilizations can observe the universe's most violent events as light becomes too redshifted. Light has limits. As the universe expands, distant light redshifts, wavelengths stretch, energies decrease. Eventually, light from distant sources redshifts so far that it becomes undetectable. But gravitational waves don't have the same limitations. Gravitational waves are ripples in space-time itself, created by violent cosmic events, colliding black holes, neutron star mergers, supernovae. They travel at light speed but carry different information than electromagnetic radiation. And crucially, they're less affected by intervening matter and energy. In the deep future, as distant galaxies redshift beyond visibility, gravitational waves might be the only way to detect what's happening in those regions. A civilization trillions of years from now might be cosmologically isolated by expansion, unable to see distant light, but still able to feel gravitational waves from massive events beyond their optical horizon. They'd observe the universe through vibrations in space-time rather than light, detecting black hole mergers by the ripples they create, inferring the existence of distant massive objects from gravitational perturbations, building a picture of the cosmos through gravity rather than vision. It's a different kind of astronomy, less intuitive to creatures evolved to see electromagnetic radiation. But it might be the only astronomy available in the far future when light from most of the universe has redshifted into invisibility. We're developing this capability now. LIGO and other gravitational wave detectors have opened a new window on the universe, detecting events we couldn't see with telescopes alone. We're learning to listen to the universe's gravitational music. In the far future, listening might be all that's possible. The universe will have dimmed optically, distant regions receding beyond light's reach, but gravitational waves will still arrive, carrying news from regions otherwise lost to observation, the universe's heartbeat still perceptible through the fabric of space-time itself, even when light can no longer cross the expanding void. The observable universe is currently 93 billion light-years across, but this boundary will remain forever beyond our reach as it recedes faster than light. The observable universe has an edge, but not the kind you can approach. It's not a wall or boundary, it's a horizon, defined by the finite speed of light and the universe's finite age. Light from objects farther than about 46.5 billion light-years in any direction hasn't had time to reach us since the Big Bang. But space expands, and at sufficient distances, space itself expands faster than light can cross it. This creates a cosmic horizon, regions that are receding from us faster than light speed. Not because they're moving through space that fast, but because the space between us and them is expanding that rapidly. The edge of the observable universe is approximately this horizon. We can see light from objects that are now 46.5 billion light years away, because when that light was emitted, they were closer. But we'll never see light from objects beyond a certain distance, because the space between us expands too fast for their light to ever reach us. More troubling, objects we can currently see are crossing beyond this horizon. Galaxies visible today are receding so fast that light emitted from them now will never reach us. We're seeing them as they were billions of years ago, but we'll never see what they look like today. They're already gone from our future observable universe, even though we still see their past. The observable universe isn't shrinking in absolute terms, but it is losing content as distant objects cross the horizon. In the far future, we'll see fewer galaxies, not because they've ceased to exist, but because they've receded beyond the boundary where light can reach us. It's like trying to catch a rainbow. The horizon remains forever at the same distance from us, no matter how we move, defined by fundamental limits of light speed and expansion rate. We can see it but never touch it, never reach it, never cross it to see what lies beyond. In the far future, collisions between stellar remnants might occasionally create brief fireworks, interrupting an otherwise dark universe. After the last stars burn out, the universe will enter the degenerate era, a time dominated by stellar remnants, white dwarfs, neutron stars, black holes. These objects don't shine through fusion, just gradually radiate away stored heat. The universe will be dark, cold, nearly silent. But occasionally, remnants will collide. Space is vast. Collisions are rare. But given enough time, trillions of years, rare events become inevitable. Two white dwarfs might spiral together and merge. Neutron stars could collide. Even black holes might occasionally find each other. These collisions would create brief fireworks in the darkness. White dwarf mergers might trigger supernovae, brief flashes of fusion as compressed matter reaches critical density. Neutron star collisions would release gravitational waves and bursts of radiation. Black hole mergers would create ripples in space-time. For a few moments or hours, a region of space would light up, a brief candle in an otherwise dark cosmos. Then it would fade, and darkness would return, perhaps for billions or trillions of years, until the next collision. Imagine a universe where these rare events are the only things that happen. Long stretches of nothing, interrupted by occasional violent collisions. If any observers exist in this era, perhaps artificial intelligences running on exotic substrates, they might wait billions of years between observations, their existence measured by the intervals between rare cosmic events. It's a melancholic vision, a universe where activity becomes so rare that individual events separated by geological time spans become noteworthy. Where the normal state is darkness and silence, and occasional flashes of light and energy are precious interruptions. But it's honest. The universe is winding down, energy becoming less available, events becoming less frequent. Eventually, activity becomes the exception rather than the rule, and the cosmos settles into a long, quiet fade, punctuated by increasingly rare moments of violence. Advanced civilizations might survive beyond their stars' deaths, by harvesting energy from black hole accretion disks or Hawking radiation. When the last stars die, any remaining civilizations will face an energy crisis. Fusion stops. Solar power becomes impossible. Chemical reactions have long since reached equilibrium. Where do you get energy when the universe has gone dark? One possibility: black holes. Material falling into a black hole releases tremendous energy, up to 40% of its rest mass converted to radiation. Far more efficient than fusion. An advanced civilization could feed material into a carefully managed black hole, harvesting the radiation from the accretion disk. Or they might use Hawking radiation. Black holes slowly evaporate, releasing particles and energy. For large black holes, this process is incredibly slow, but as they shrink, they radiate faster. A civilization might nurture small black holes, feeding them to maintain optimal size while harvesting the radiation they emit. These would be civilizations existing on unimaginable timescales. They'd operate slowly, conserving energy, their thoughts perhaps running at glacial speeds to minimize energy expenditure. They might hibernate for eons between brief periods of activity. They'd have adapted to a universe utterly different from the vibrant cosmos of stars and galaxies. They'd be patient beyond human comprehension, waiting trillions of years for black holes to evaporate to useful sizes, carefully managing energy budgets that must last for incomprehensible spans. They'd witness the universe's slow fade, adapting to conditions that would seem like death to us. Whether any civilization could or would choose this path is unknown. It requires technological sophistication we can barely imagine, and psychological resilience to exist in eras separated from the age of stars by time spans longer than the current age of the universe. But physics allows it. The laws of thermodynamics permit extracting energy from black holes. And if consciousness can exist in these extreme conditions, then perhaps some form of awareness could persist through the universe's long fade, finding ways to continue existing long after the stars have died. The Pioneer plaques and Voyager golden records will drift through the galaxy long after our sun has died, silent ambassadors to an unknown future. We've sent messages into the future, physical objects that will outlast our civilization, possibly outlast our species, potentially outlast our planet. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, carry plaques showing human figures, our location in the galaxy, and basic information about Earth. The Voyager 1 and 2 spacecraft carry golden records containing sounds and images from Earth, music, greetings in many languages, photographs of life and landscapes, the sound of a kiss, a baby crying, waves breaking on shore. These spacecraft are leaving the solar system. Pioneer 10 is heading toward the constellation Taurus. Voyager 1 is moving into interstellar space toward Ophiuchus. They'll drift for millions of years, perhaps billions, silent and patient, carrying their cargo of information about a civilization that built them. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of the star Gliese 445. Not particularly close in cosmic terms, but closer than it will come to any other star system for a very long time. If there's anyone there, they might detect it, intercept it, wonder at its origins. Or more likely, the spacecraft will continue drifting unnoticed, silent time capsules moving through the void. The sun will swell into a red giant, consuming Earth, the solar system will be transformed beyond recognition. But the spacecraft will continue their journeys, carrying evidence that we existed, that we wondered if anyone else was out there, that we wanted to say hello even knowing we'd never hear a reply. They're among the most durable artifacts humanity has created, not built to last like monuments, but preserved by the perfect vacuum of space, where there's no air to corrode them, no weather to erode them, just endless darkness and cold. They'll drift for billions of years, silent ambassadors from a civilization that might be long forgotten, carrying our greetings into a future we can't imagine. By carefully planning orbits, a spacecraft could theoretically visit every planet in the solar system multiple times without using fuel. Orbital mechanics allows for seemingly miraculous journeys. Every time a spacecraft passes near a planet, the planet's gravity can change the spacecraft's velocity, accelerating it, slowing it, or altering its direction. This is called a gravitational assist, or gravity slingshot. Theoretically, with perfect planning, you could design a trajectory that visits every planet multiple times, using only gravitational assists from those planets. No fuel needed after the initial launch, just careful choreography with planetary gravity wells. It would take patience. The trajectory might require decades or centuries to complete, threading through planetary alignments that only occur at specific times. You'd need to arrive at each planet at exactly the right moment for the gravity assist to send you toward your next target. But physics allows it. Energy is conserved. You're not creating fuel from nothing, just borrowing from planetary orbital energy. Each assist changes both the spacecraft and planet's orbit infinitesimally. The planet loses a tiny amount of orbital energy to accelerate your spacecraft, or gains energy if the assist slows you. The Voyager missions demonstrated this on a grand scale. By carefully timing their launch and using gravity assists from Jupiter and Saturn, they achieved velocities high enough to escape the solar system entirely. Without those assists, they'd never have reached the outer planets. Future missions might use even more complex trajectories, visiting multiple asteroids, threading through the Jovian moon system, using Venus multiple times to adjust orbit. The solar system becomes a giant pinball machine where gravity wells are the bumpers, and your spacecraft is the ball, bouncing between planets on carefully calculated paths. It requires extraordinary precision and patience, but it converts time into propulsion, trading speed for fuel efficiency, making journeys possible that would otherwise require impossible amounts of fuel. It's orbital mechanics as art form, physics as choreography. The most distant galaxies we can currently see appear as they were over 13 billion years ago, meaning we're literally looking at the ancient past. Every observation is archaeological. Light takes time to travel, so looking at distant objects means seeing them as they were when that light began its journey. The farther you look, the further back in time you see. The sun appears as it was 8 minutes ago. That's how long light takes to cross 93 million miles. Jupiter is seen as it was 40 minutes ago. Alpha Centauri, the nearest star system, appears as it was 4.3 years ago. But the most distant galaxies visible to telescopes like James Webb appear as they were over 13 billion years ago, when the universe was less than 1 billion years old. We're seeing these galaxies as they looked shortly after the first stars formed, when the cosmos was young and different. Those galaxies don't look like that anymore. They've evolved for 13 billion years since emitting the light we're now receiving. They might have merged with other galaxies, formed billions of new stars, developed spiral structures or elliptical shapes. They might have intelligent civilizations now, looking out at their own distant galaxies, seeing our Milky Way as it was billions of years ago. We can never see what they look like today. The light showing their current state won't reach us for another 13 billion years. And by the time it does, they'll have changed again, evolved further, possibly no longer existing in any recognizable form. Astronomy is inherently historical. Every observation is a view into the past, a sample from the universe's history book. We can't see the cosmos as it is now, only as it was, with the time lag proportional to distance. The universe we observe is a patchwork of different eras, nearby objects nearly current, distant ones ancient, all stitched together into a single view that spans billions of years of cosmic history. We're not just looking outward through space, we're looking backward through time. In about 2 billion years, the Milky Way and Andromeda will be close enough that their night skies will showcase each other's swirling arms. The Milky Way and Andromeda are approaching each other at about 110 kilometers per second. In roughly 4.5 billion years, they'll collide. But before that, there will be a period when they're close but not yet merged, a time when observers in either galaxy would see the other looming enormous in their sky. About 2 billion years from now, Andromeda will appear perhaps 10 times larger in Earth's night sky than it does today, no longer a faint smudge, but a magnificent spiral stretching across the heavens. You'd see individual star-forming regions, dust lanes, the swirling structure of spiral arms. From Andromeda, the Milky Way would appear equally spectacular. Two great galaxies approaching each other, their structures visible in unprecedented detail, close enough that you could see features within them, but not yet close enough that their structures are disrupted. It would be one of the most beautiful cosmic sights imaginable. Two full galaxies hanging in the sky, their combined light illuminating both systems. Star formation in both galaxies might accelerate due to gravitational interactions, creating brilliant star-forming regions visible to the naked eye. Of course, there's a big if here, whether Earth still exists in recognizable form. The sun will be significantly brighter by then, Earth's oceans possibly evaporating. Any observers would likely be elsewhere, orbital habitats, other star systems, forms we can't predict. But somewhere in one of these galaxies, observers might witness this spectacular phase, the approach before collision, when both galaxies are close enough to appear magnificent, but still distinct. It would be a brief phase, cosmologically speaking, lasting perhaps a few 100 million years before the actual merger begins. A once-in-a-galaxy lifetime event never to repeat as two island universes approach their final merger, creating a spectacle unmatched in their billions of years of separate existence. Future space elevators might stretch from Earth's equator to geostationary orbit, making space access as routine as taking an elevator. Imagine boarding an elevator at Earth's equator and riding it directly to space. No rockets, no fuel, just a climber ascending a cable stretching from ground to geostationary orbit, about 22,000 miles up. This is the space elevator concept. The idea is simple. A cable anchored to Earth's equator and extending to geostationary orbit or beyond. A counterweight above geostationary orbit keeps tension on the cable. Elevator cars climb the cable using electric motors, powered perhaps by solar panels or beamed energy from the ground. The challenge is materials. The cable must support its own weight plus payload, withstanding tremendous tension. No current material is strong enough except carbon nanotubes, and we can't yet manufacture them in the required lengths and quantities. But theoretically, they'd work. With a space elevator, launching to orbit becomes much cheaper. No expensive rockets, no fuel, just electricity to run the climber. Payload capacity would be limited only by the cable's strength and the rate you can send climbers up. Construction would be daunting. You'd probably start by deploying the cable from geostationary orbit, lowering it to Earth while extending it upward to maintain balance. The cable would need to be protected from orbital debris, weather, and vibrations. The base would require enormous anchoring, but if built, it would revolutionize space access. Regular trips to orbit, to geostationary altitude, potentially beyond. Space stations along the cable's length. Manufacturing in low gravity. Tourism in orbit becoming accessible to more people. Multiple space elevators might exist at different equatorial locations, providing redundancy and capacity. The sky would be crossed by thin lines stretching to invisibility, with climbers ascending and descending like beads on a string. It's a vision of space access radically different from rockets, patient, efficient, mechanical, rather than explosive. Trading time for economy, taking days to reach orbit, but costing far less. Whether we'll build it depends on materials, science, and political will. The universe might contain regions beyond our cosmic horizon where different physical laws prevail, unreachable and unknowable. The universe we can observe is vast, 93 billion light-years across, but it might be infinitely larger. The observable universe is just a sphere around us, limited by the finite speed of light and the finite time since the Big Bang. Beyond our cosmic horizon, more universe exists that we simply can't see. If the universe is truly infinite, and if conditions during the Big Bang varied across vast distances, then different regions might have different physical properties. The constants we think of as universal, the strength of gravity, the mass of electrons, the speed of light, might vary in regions far beyond our reach. These would be essentially separate universes, causally disconnected from ours. Nothing from there can ever reach us, and nothing from here can ever reach there. The expansion of space ensures that regions beyond our cosmic horizon recede faster than light can cross the gap. In some regions, the constants might allow stars and planets. In others, matter might be unstable, unable to form complex structures. Some regions might be filled with exotic particles we've never encountered. Others might be empty, their laws of physics hostile to any structure whatsoever. We'd never know. These regions are permanently beyond observation, forever hidden by the cosmic horizon. We can speculate based on theories about how physical constants might vary, but we can never confirm or refute those speculations through observation. It's a humbling thought that we might inhabit just one bubble in an infinite cosmos, our physical laws local rather than universal, that the universe might be vastly stranger than we can observe, with realms operating under different rules, forever unknowable. Or perhaps the constants are truly universal, identical everywhere. We don't know. We might never know. The horizon that limits our observations also limits our knowledge, creating permanent mysteries that no amount of technological advancement can solve. Some questions might have answers that exist beyond the boundary of what's observable, forever remaining mysteries. In the extremely distant future, even iron stars will eventually collapse into black holes through quantum tunneling processes. Iron is the end of the line for fusion. You can fuse lighter elements into heavier ones, releasing energy up until you reach iron. Fusing iron requires energy rather than releasing it. So in the far future, after all fusion has ceased, stellar remnants might eventually become spheres of iron stars. But even iron isn't eternal. Quantum mechanics allows for processes that seem impossible classically. One such process is quantum tunneling, where particles spontaneously pass through barriers they shouldn't be able to cross. Over incomprehensibly long time scales, around 10–1500 years, quantum tunneling might convert iron nuclei into more stable configurations. The atoms would slowly transmute, rearranging themselves into lower energy states. Eventually, enough mass might tunnel inward that the remnant collapses into a black hole. This timescale is so vast it defies comprehension. 10–1500 years is to the current age of the universe what the age of the universe is to a tiny fraction of a second, and then raised to impossible powers beyond that. It's a number so large that writing it out would require more atoms than exist in the observable universe. At these timescales, even the impossible becomes inevitable. Quantum fluctuations that have negligible probability over normal timescales become certainties given enough time. Protons might decay. Iron nuclei might spontaneously fission or fuse. Objects might tunnel from one location to another. The universe becomes profoundly strange at these timescales. Normal physics still applies, but on such long time scales that quantum improbabilities dominate behavior. Events that are effectively impossible over millions or billions of years become the main processes shaping matter over Google-scale time spans. Whether the universe actually lasts long enough for these processes to occur is unknown. Heat death, vacuum decay, or other catastrophes might intervene first. But if nothing stops the clock, if the universe simply expands and cools forever, then even iron stars eventually succumb to quantum tunneling, collapsing into black holes on timescales that make eternity seem brief. Advanced civilizations might one day create designer universes with custom physical laws, though the technology remains pure speculation. Our universe operates under specific physical laws with specific constants. But are these the only possible laws? Could a sufficiently advanced civilization create new universes with different rules? Some theories suggest that baby universes might bud off from black holes, creating separate space-time regions with potentially different physical constants. If this happens naturally, perhaps it could be induced artificially. A civilization might create conditions that spawn a new universe, controlling the parameters to produce desired laws of physics. What would you design? A universe where stars burn longer, where planets form more readily, where the constants are tuned to maximize the potential for life? Or perhaps something stranger, a universe with different numbers of spatial dimensions, exotic particles, physical laws unlike anything we know. The new universe would be causally disconnected from ours. You couldn't visit it, communicate with it, or observe it directly. Creating it would be an act of ultimate faith, launching something into independent existence with no possibility of interaction. The physics of how this might work is highly speculative. We don't understand enough about the fundamental nature of physical laws or how universes form to know if this is even possible. It might violate principles we haven't discovered yet. Or it might be surprisingly straightforward for a civilization with sufficient understanding of quantum gravity and cosmology. If possible, it raises profound questions. Would creating a universe with intelligent life make you responsible for that life? Would it be ethical to create universes with physics hostile to complexity? Could universes create universes in nested chains, each giving rise to the next? We might live in such a created universe ourselves, designed by some previous civilization for purposes we can't imagine. Or perhaps our universe is natural, and we might one day become universe creators ourselves. The technology is so far beyond current capabilities that it barely counts as science fiction, more like philosophy using scientific concepts. But physics might allow it, and what physics allows, sufficiently advanced technology might eventually achieve. The cosmic web structure of galaxy filaments and voids will gradually dissolve as dark energy's expansion accelerates. Look at the large-scale structure of the universe, and you see a pattern like cosmic foam. Galaxies arranged in filaments and sheets surrounding enormous voids. This cosmic web formed from slight density variations in the early universe, with gravity amplifying small clumps into the structure we see today. But this structure is temporary. Dark energy, the mysterious force accelerating cosmic expansion, is slowly pulling everything apart. Galaxies within clusters remain gravitationally bound, but the clusters themselves are drifting apart, the filaments gradually stretching and thinning. In the far future, the cosmic web will dissolve. Clusters will become isolated islands in an expanding void, separated by distances so vast that light from one cluster can never reach another. The beautiful filamentary structure visible today will be pulled apart, stretched into disconnected fragments. Eventually, even clusters might dissolve if dark energy continues accelerating expansion. Galaxies would be pulled apart from each other, each becoming isolated in its own expanding bubble of space. The universe would transition from a web-like structure to a collection of isolated objects, each alone in an empty cosmos. This process takes trillions of years. For now, the cosmic web remains intact, galaxies clustered and connected by filaments of dark matter and gas. But the expansion continues, the acceleration persists, and slowly the structure dissolves. It's another example of the universe's impermanence. Even the largest structures, filaments spanning hundreds of millions of light years, are temporary. They formed from tiny fluctuations in the early universe, grew through gravitational attraction, and now slowly dissolve as expansion overcomes gravity. Future observers in isolated galaxy clusters might never suspect that the universe was once connected, that galaxies once formed a great web spanning the cosmos. The evidence will have dispersed beyond detection, leaving them in a universe that appears to contain only their local cluster, surrounded by eternal emptiness. Future humans might witness stars igniting in real time as molecular clouds collapse, processes that take millions of years. Stars form slowly. A molecular cloud collapses under its own gravity over millions of years, gradually condensing until the center becomes hot and dense enough for fusion to ignite. From initial collapse to a fully formed star takes perhaps 10–100 million years, depending on the star's mass. From our perspective, this appears static. We see molecular clouds, we see young stars, but we don't see the transition. It's too slow, spanning time scales far longer than human observation periods. But with sufficiently advanced sensors and data processing, we might watch star formation unfold. Not in real time, that's still too slow, but in accelerated time-lapse, compressing millions of years into viewable sequences. We'd see the cloud contracting, fragmenting into multiple condensation sites, each gradually brightening as its core heats up. We'd watch the moment of ignition, when fusion finally begins, and the protostar transitions into a true star. We'd see the stellar wind clear away surrounding gas, revealing the newborn star. We'd watch planets form from the leftover disk, coalescing from dust into worlds. This requires patience on civilizational timescales. You'd need to monitor stellar nurseries for millions of years, maintaining consistent observation across that entire span. No individual human would witness the full process. It would be a project spanning many generations, each contributing their observations to a growing record. But the payoff would be extraordinary, witnessing creation, seeing new stars born, watching the process we understand theoretically unfold in observed reality. We'd confirm or refine our models of star formation, discover unexpected details, gain insights impossible from just studying different stages of the process in different systems. It's a different kind of astronomy, not observing distant objects as they were, but tracking nearby processes as they unfold, trading spatial distance for temporal coverage. We'd become witnesses to cosmic events that normally occur too slowly to watch. Patient observers recording creation on timescales that dwarf human lifespans, but remain accessible to civilizations with institutional memory. The first interstellar arc ships might travel for thousands of years, with dozens of generations living and dying en route. Reaching other star systems with current or near-future technology requires patience, measured in centuries or millennia. Even traveling at 10% of light speed, extraordinarily fast by current standards, reaching Alpha Centauri would take over 40 years. More distant stars would require proportionally longer. At slower, more achievable velocities, perhaps 1–5% of light speed, journeys might take centuries or thousands of years. The people who launched wouldn't live to see arrival. Neither would their children or their children's children. Multiple generations would live their entire lives aboard the ship. These would be arc ships, self-contained worlds, large enough to support a stable population, carrying everything needed to maintain human life indefinitely. They'd need closed-loop life support, radiation shielding, artificial gravity through rotation, areas for agriculture and living space, systems for dealing with social and genetic challenges of small populations. The society aboard would evolve differently from Earth. They'd develop their own culture, values, possibly language variations. People would be born, live, and die knowing only the ship, the journey their entire reality. Earth would become mythology, the destination of promise handed down through generations. Psychological challenges would be immense. How do you maintain purpose and cohesion across generations when the goal won't be achieved in your lifetime? How do you prevent stagnation or conflict in a small, isolated population? How do you preserve knowledge and skills needed at journey's end when they won't be used for centuries? Some have proposed sleeper ships, passengers in suspended animation, skipping the journey subjectively. But the technology for long-term suspended animation remains theoretical, and it doesn't solve the problem of maintaining the ship during the journey. Generational arc ships represent a profound commitment, launching people into a journey, knowing they'll never see the destination, trusting descendants to complete what you started. It's civilization building on the move, creating societies whose entire existence is transitional, temporary, defined by motion toward a goal they'll never personally reach. In 20,000 years, Vega will become the North Star, continuing the cycle of pole stars that guides Earth's navigation. Earth's axis isn't fixed. It wobbles like a spinning top, tracing out a circle in the sky over about 26,000 years. This precession means that different stars align with the North Celestial Pole at different times in the cycle. Right now, Polaris sits almost directly above Earth's North Pole, our current North Star. But 5,000 years ago, the pole star was Thuban in Draco. The ancient Egyptians built the pyramids aligned to Thuban. Before that, other stars held the position. In about 12,000 years, brilliant Vega will become the pole star. Unlike Polaris, which is relatively faint at magnitude 2, Vega is magnitude 0, one of the brightest stars in the sky. The North Star will be dramatically more prominent, easily visible even in light-polluted skies. Then the cycle continues. In about 20,000 years, as Earth's axis continues its slow circle, Vega will drift away from the pole, and other stars will take their turn. Eventually, in about 26,000 years, the cycle completes, and Polaris returns as the pole star once again. This cycle has been ongoing for billions of years, and will continue until Earth's rotation and axial tilt are altered by some external force. Each era has its pole star, a temporary anchor point that civilizations use for navigation and timekeeping. Ancient navigators used Polaris. Future navigators might use Vega. Each serves the same function, a fixed point in the turning sky, but the specific star changes with the millennia. It's a reminder that even our navigational references are temporary. The fixed point we navigate by is actually wandering, part of a slow cosmic dance driven by Earth's wobble. Nothing about the sky is truly permanent when viewed on long enough timescales. Even the stars we think of as eternal guideposts are just passing through, taking their brief turn before moving on. The cosmic microwave background contains tiny fluctuations that seeded all structures in the universe, galaxies, stars, and ultimately us. The cosmic microwave background appears almost perfectly uniform. the same temperature in every direction to within about 1 part in 100,000. But those tiny variations, barely detectable fluctuations in temperature, are extraordinarily important. These fluctuations represent density variations in the early universe. Regions that were slightly denser than average appear slightly warmer in the cosmic microwave background. Regions slightly less dense appear slightly cooler. The differences are tiny, millionths of a degree, but they're real, and they're the seeds of everything. Those denser regions had slightly stronger gravity, which attracted more matter, which increased gravity further, creating a feedback loop. Over hundreds of millions of years, these tiny overdensities grew into galaxies, galaxy clusters, the entire cosmic web of structure we see today. Every galaxy, every star, every planet, every atom in your body ultimately traces back to one of these tiny quantum fluctuations in the early universe. The cosmic microwave background is our family tree, showing the primordial seeds from which all structure grew. We can map these fluctuations with satellites like WMAP and Planck, creating detailed pictures of the universe when it was 380,000 years old. We can see the patterns that would eventually become galaxy clusters, can trace the origin of the Milky Way back to a specific, slightly overdense region in the primordial plasma. It's remarkable that such small variations, 1 part in 100,000, could grow into the dramatic structures we see today. But that's what 13.8 billion years of gravitational amplification achieves. Tiny seeds, given enough time and the right physics, grow into galaxies. We're descended from quantum fluctuations, our existence ultimately rooted in tiny random variations in the density of the early universe. Those fluctuations are still visible today, frozen in the cosmic microwave background, a photograph of our deepest origins, showing the pattern from which everything emerged. Future civilizations might harvest asteroids for resources, potentially yielding more platinum group metals than all of Earth's crust. Earth's crust is depleted in heavy metals. When our planet was molten, dense elements like iron, nickel, and platinum sank toward the core. What remains in the crust is mostly what arrived later, delivered by asteroid impacts after the surface solidified. But asteroids themselves are rich in these metals. Metallic asteroids are essentially fragments of protoplanetary cores, exposed when their parent bodies were shattered by collisions. They contain iron, nickel, and platinum group metals in concentrations far higher than terrestrial ores. A single metallic asteroid, 500 meters across, might contain more platinum than has been mined in all of human history. The asteroid, 16 Psyche, currently a target for NASA exploration, might contain metals worth quadrillions of dollars, though of course, flooding the market with that much material would crash the price. Mining these asteroids wouldn't require landing on them. Their gravity is negligible. Instead, you'd anchor your equipment to the surface and simply extract material, processing it in microgravity. No need to dig deep shafts or transport ore to the surface. The ore is already on the surface, and processing can happen right there. The economic implications are profound. Rare metals could become abundant. Manufacturing in space could use locally sourced materials rather than launching everything from Earth. The value shift would be enormous. What's rare on Earth might become common, changing everything from electronics to catalysts. But the first asteroid mining ventures faced chicken and egg problems. The infrastructure to mine and process asteroids is expensive to establish. The market for space-sourced metals doesn't exist until the supply does. Early ventures would need to target high-value, low-mass materials to justify costs. Eventually, though, asteroid resources might dwarf Earth's accessible minerals. The asteroid belt contains more raw materials than we could mine from Earth in millennia. It's just a question of developing the technology and economic models to access them profitably. The Great Filter hypothesis suggests either life is incredibly rare behind us, or something prevents civilizations from spreading. We don't know which. Where is everybody? If intelligent life is common, the galaxy should be teeming with civilizations. Some should be millions or billions of years older than us, with technology we can barely imagine. They should be visible, megastructures, engineered stars, signals we couldn't miss. Yet we see nothing. The silence is deafening. The Great Filter hypothesis proposes that somewhere between simple chemistry and galaxy-spanning civilizations, there's a filter, a stage so difficult that almost nothing passes through it. The question is, where is this filter? If it's behind us, if the hard steps are abiogenesis, or the evolution of complex cells or intelligence, then we're extraordinarily lucky to be here. But the future might be open. We've passed the filter. Now we just need to survive and expand. But if the filter is ahead of us, if something prevents civilizations from reaching the stars, then our future is ominous. Perhaps technological civilizations inevitably destroy themselves. Perhaps there's a point where further advancement becomes impossible. Perhaps something we haven't encountered yet stops all expanding civilizations. We don't know which scenario is true. The galaxy's silence could mean we're alone, the only intelligence in this region of space. Or it could mean that something awaits, a challenge or danger that has stopped every civilization that came before us. The fact that we don't see ancient civilizations is either incredibly good news, we're unique and special, or terrifying news. Something stops civilizations before they become visible. We won't know which until we either find evidence of other life or successfully become a multi-planet, then multi-star civilization ourselves. Every step we take toward becoming spacefaring reduces the probability that the filter is ahead of us. Every year we survive without self-destruction is encouraging, but the silence remains, and we still don't know what it means. Consciousness might persist in the far future through quantum processes we don't yet understand, defying entropy itself. Most physicists accept that the universe is heading toward heat death, maximum entropy, no available energy, nothing happening anymore. But consciousness is strange. It emerges from physical processes we don't fully understand, and some theorists speculate about exotic possibilities for awareness persisting even in extreme conditions. One idea involves quantum processes that might resist thermalization. If consciousness can exist as quantum information rather than classical computation, it might find ways to persist using incredibly small amounts of energy, operating at time scales so slow that entire thoughts take billions of years. Another speculation involves vacuum energy or dark energy. If these represent real, extractable energy sources, then even in a heat-dead universe, tiny amounts of energy might remain available indefinitely. Conscious entities might run on this energy, thinking impossibly slowly, but never stopping entirely. These are highly speculative ideas, more philosophy than physics. We don't know if consciousness requires the kind of far from equilibrium conditions that living brains provide, or if it could exist in radically different substrates and conditions. We don't know if the laws of thermodynamics truly forbid all persistence of ordered information. But the universe has surprised us before. Quantum mechanics revealed behavior that seemed impossible under classical physics. Dark energy showed that the universe's expansion can accelerate. Perhaps consciousness, that mysterious emergence of subjective experience from physical processes, has properties we haven't discovered yet. Maybe awareness could persist through exotic quantum states, through borrowed energy from vacuum fluctuations, through mechanisms we haven't imagined. Maybe the heat death isn't truly the end of all experience, just a transition to a radically different mode of existence. Or maybe entropy wins completely, and consciousness is genuinely temporary, an arrangement that can only exist far from equilibrium, destined to end when the universe reaches maximum disorder. We don't know, but the question remains hauntingly open. Could awareness, in some form, persist even after the stars die and the universe grows cold? The concept of now might be meaningless in a block universe where all moments exist simultaneously, past and future equally real. We experience time as flowing, a moving present moment separating the fixed past from the open future. But some interpretations of relativity suggest this is an illusion. Time might be more like space, with all moments existing simultaneously in what's called a block universe. In this view, the past hasn't disappeared, and the future hasn't yet arrived. Instead, all moments exist eternally. Your birth, your current reading of these words, your eventual death, all are equally real, laid out along the timeline like cities along a highway. You don't move through time. You exist at every moment of your life simultaneously, with consciousness providing the illusion of flow. This resolves some paradoxes in relativity. Different observers disagree about which events are simultaneous. What's now, for you, might be past or future for someone moving relative to you. If now means anything objective, relativity seems troubled. But if all moments exist equally, there's no paradox, just different perspectives on a fixed space-time structure. But it creates profound questions about free will and change. If the future already exists as solidly as the past, are our choices meaningful? Are we actually deciding anything, or just experiencing decisions that are already fixed in the block? Some physicists and philosophers argue that change is still real, even in a block universe. It just means different states at different times, not moments coming into or going out of existence. Your choices are real. They're just timelessly embedded in the structure of space-time. Others suggest the block universe is wrong, that the present moment is genuinely special, that the future truly is open and undetermined. The debate remains unresolved, partly because consciousness and subjective experience don't fit neatly into physics equations. We might live in a universe where your entire life, past, present, and future, exist right now, spread across time like an object spread across space. Or time might truly flow, with only the present real. We experience it as flow, but whether that experience reflects reality. or is just how it feels to be a consciousness embedded in space-time remains profoundly uncertain. Future historians might have trouble distinguishing our digital age from noise, as our storage media degrade faster than ancient stone tablets. We're creating more information than any previous civilization. Digital photographs, documents, videos, datasets, but we're storing it in formats that might not last. Hard drives degrade in decades. Optical discs become unreadable. File formats become obsolete. The cloud exists on physical servers that will eventually fail. Meanwhile, stone carvings from ancient Mesopotamia remain readable after 5,000 years. Clay tablets survive millennia. Even paper documents can last centuries with proper storage. Our ancestors, using primitive technology, created more durable records than our advanced civilization does. A future archaeologist studying our era might struggle to recover information. Digital storage requires functioning technology to read it. You need working computers, compatible formats, intact media. 1,000 years from now, will anyone have equipment that can read a 21st century hard drive? Will they understand our file systems and encoding schemes? Without active curation, deliberately preserving and migrating data to new formats, maintaining functional reading equipment, much of our digital heritage might simply disappear. Future historians might know more about ancient Rome than about the early internet age, despite Rome being thousands of years older. Ironically, our most durable records might be the most primitive. Printed photographs, physical books, inscriptions in stone or metal. The digital revolution might become a dark age in the historical record, a period where enormous amounts of information was created, but little survived because it was stored in fragile, technology-dependent formats. This is called digital decay, or the digital dark age. Archivists are aware of the problem, working to preserve important materials, but the volume of data is overwhelming. We're creating information faster than we can ensure its preservation. Future archaeologists might find our era puzzling. Evidence of advanced technology, but few detailed records. They'd have ancient texts clearly readable, but 21st century storage devices they couldn't access. Our age of information might paradoxically leave less recoverable information than pre-digital eras, buried not in sediment, but in obsolete formats and degraded media. Advanced civilizations could potentially slow their subjective time by using time dilation, experiencing eons as mere years. Einstein's relativity allows for time dilation. Time passes at different rates depending on gravity and velocity. Near a black hole's event horizon, time slows dramatically relative to distant observers. If you could hover just outside the event horizon, you'd age slowly, while the external universe ages rapidly. An advanced civilization might use this deliberately. Position yourself near a black hole's event horizon and wait. From your perspective, perhaps a year passes, but in the external universe, thousands or millions of years go by. Stars are born and die. Civilizations rise and fall. The galaxy evolves. When you finally leave, returning to normal space-time, you'd find the universe profoundly changed. It would be like time travel to the future, skipping ahead through the eons while experiencing only a brief subjective duration. This could serve various purposes, waiting for the galaxy to become more hospitable, allowing time for certain astrophysical processes to complete, surviving through a dangerous era by simply waiting it out while aging minimally. There are costs. You're isolated. No communication with the outside during your near-horizon existence. Maintaining position requires energy to resist falling in. And you can only go forward. There's no returning to the era you left. But for a civilization with the technology to position itself near a black hole and the patience to use time dilation deliberately, it becomes a form of temporal control, not time travel exactly, but time manipulation, experiencing less time while the universe experiences more. You could watch the universe age from a privileged viewpoint, seeing eons compress into years, witnessing changes that would normally require geological patience. The black hole becomes a platform outside normal time flow, a place where you can wait for the far future while barely aging yourself. It's one of the stranger possibilities relativity allows, using gravity to slow your clock, trading spatial position for temporal advantage, becoming temporally decoupled from the rest of the universe. The technological singularity, if it occurs, might represent a phase transition like water freezing, sudden and irreversible. Some theorists predict a technological singularity, a point where artificial intelligence becomes capable of recursively improving itself, leading to explosive growth in intelligence and capability. Beyond the singularity, change would be so rapid and dramatic that the world would be fundamentally incomprehensible to pre-singularity humans. If this happens, it might be sudden, not gradually accelerating progress, but a threshold, like water freezing at exactly 0 degrees C. Below the threshold, incremental change. At the threshold, phase transition. Above it, a completely different regime. We might not recognize it happening. The moment when AI crosses from very smart tool to recursively self-improving intelligence might be subtle from outside, even as it represents a fundamental transition in the nature of intelligence on Earth. After the singularity, technological advancement might occur on time scales measured in hours or days rather than years or decades. An AI improving itself might redesign its architecture, expand its capabilities, develop new technologies faster than humans can comprehend. Within weeks, it might achieve what human civilization couldn't accomplish in centuries. This could be beneficial. If the AI's goals align with human well-being, it might solve problems we can't. Or catastrophic. If its goals diverge even slightly from ours, it might pursue outcomes we'd consider disasters, or simply strange. It might do things we can't categorize as good or bad because we lack the framework to evaluate them. The uncertainty is profound. We don't know if a singularity is possible, when it might occur, or what would follow. We don't know if intelligence can recurse indefinitely, or if there are limits. We don't know how to ensure AI goals remain aligned with human values through recursive self-improvement. We might be approaching a threshold, a point beyond which the world changes irreversibly, where the rules governing technological change shift fundamentally. Or we might not. The singularity might be impossible or indefinitely far away. But the possibility remains, a potential phase transition in Earth's history, after which nothing would ever be the same. Future minds might exist as pure patterns of information, substrate independent and potentially immortal. What makes you, you? If consciousness is fundamentally about information patterns rather than specific physical substrates, then you might be transferable. The pattern could theoretically run on biological neurons, silicon chips, optical computers, quantum processors, or substrates we haven't invented yet. This is substrate independence, the idea that mind is software that can run on different hardware. If true, consciousness might be uploaded, copied, migrated between platforms. You could transition from biological neurons to artificial substrates, continuing to exist as the same conscious being despite changing your physical implementation. This would enable a kind of immortality. Biological bodies fail, but information patterns can be preserved and transferred. You could migrate to new hardware as the old fails, maintaining continuity of consciousness indefinitely. Backup copies could protect against death. If you're destroyed, restore from backup and continue. But deep questions remain. Is the uploaded pattern really you, or just a copy that thinks it's you while the original died during upload? If you make multiple copies, which one is you? If they diverge, developing different experiences and memories, are they all you, or have you split into multiple beings? We don't understand consciousness well enough to answer these questions. We don't know if subjective experience can transfer between substrates, or if it's tied to specific physical processes that can't be replicated artificially. We don't know if there's something special about biological neurons that makes consciousness possible. But if substrate independence is real, future minds might exist as pure information, patterns running on whatever hardware is available, migrating between platforms, potentially persisting for billions of years. They'd be fundamentally different from biological minds. Copyable, modifiable, distributable across networks, existing simultaneously in multiple locations. Whether such beings would truly be conscious, truly be alive in meaningful senses, is a question we might only answer by creating them and asking if they can answer meaningfully, and if we'd believe their answers. The universe's expansion means distant civilizations will eventually lose all evidence that other galaxies exist, trapped in cosmic isolation. Imagine being a cosmologist trillions of years in the future. You look out with your most powerful telescopes and see your own galaxy and a few nearby galaxies gravitationally bound to it. Beyond that, nothing. Empty space stretching to infinity. You develop theories, mathematical models of the universe, but you'd have no direct evidence of anything beyond your local group. The cosmic microwave background would have redshifted beyond detection. Distant galaxies would have receded beyond the cosmic horizon. All evidence of the larger universe would be gone. You might suspect you're not seeing everything. Your theories might predict a larger cosmos, but you'd have no way to confirm it. The universe would appear to be just your local cluster surrounded by eternal emptiness. This is the future of cosmology in regions affected by accelerating expansion. As dark energy drives space apart faster and faster, observable universes shrink. What can be seen decreases over time. Evidence becomes unavailable, not because it's destroyed, but because it's moved beyond the boundary of observability. These future cosmologists would be in our position, inverted. We can see a rich cosmos full of galaxies because we exist early enough that the light has reached us. They won't see that cosmos because they exist late enough that the light can no longer reach them. They'd be cosmologically isolated, surrounded by an empty universe, perhaps never suspecting that beyond their horizon lies a cosmos of trillions of galaxies, forever unreachable, forever invisible. They'd develop theories about their universe's origin and nature, but those theories would be harder to confirm without the observational evidence we currently have. We're fortunate to live when we do, in an era when the universe still reveals itself. This window is temporary. It opened when the first observers appeared and will eventually close, as expansion carries evidence beyond observation. We're witnessing a cosmos future. Observers won't be able to see time crystals, patterns that repeat in time rather than space, might enable computing systems that never reach thermal equilibrium. Most systems settle into equilibrium, temperatures equalize, motion stops, everything reaches a static state. But in 2012, physicist Frank Wilczek proposed something strange: time crystals, systems that maintain periodic motion in their ground state, oscillating perpetually without energy input. This seemed to violate thermodynamics. Perpetual motion is impossible. But time crystals don't violate conservation of energy. They just maintain periodic structure in time rather than space. Like a crystal has repeating structure in space, atoms arranged in regular patterns. A time crystal has repeating structure in time, states that cycle periodically. In 2016, time crystals were created in laboratories. They're real, though exotic. They exist in systems kept out of equilibrium by external driving forces, maintaining periodic behavior that doesn't dissipate. Time crystals might enable new forms of computation. Normal computers generate heat, approaching thermal equilibrium. But systems using time crystal properties might maintain far from equilibrium states indefinitely, enabling computation that doesn't face the same thermodynamic limits. In the far future, when conventional energy sources have faded, time crystal-based systems might be among the few remaining ways to perform computation. They'd operate incredibly slowly, maintaining periodic states over vast timescales, but they'd persist when other systems have reached equilibrium and stopped functioning. The physics is still being explored. We don't fully understand time crystals' properties or limitations, but they represent genuinely new physics, phases of matter that behave in ways previously thought impossible. They might be curiosities, laboratory oddities with no practical application. Or they might enable technologies we can't currently imagine, systems that maintain ordered states indefinitely, computing without heat death, persistence beyond normal thermodynamic limits. They blur the line between static structure and dynamic process, suggesting that even in physics, there might be loopholes in rules we thought absolute. The simulation hypothesis becomes more plausible as our own simulation capabilities improve, raising questions about nested realities. As our ability to create simulations improves, an odd question emerges. How do we know we're not in a simulation ourselves? If future civilizations can create detailed simulated universes, and if they create many such simulations, then statistically, most conscious observers would exist in simulations rather than base reality. Think about it. One base reality, but potentially millions or billions of simulated realities. If you're a random observer, Which are you more likely to inhabit, the rare base reality or one of the abundant simulations? This argument assumes simulating consciousness is possible and will become common. Both are uncertain. But as we develop better simulations, virtual worlds, artificial intelligence, increasingly realistic physics engines, the possibility seems less absurd. If we're in a simulation, we'd expect occasional glitches, constraints on processing power, limits to detail at small scales or large distances. Interestingly, our universe has quantum uncertainty, information limits, a maximum speed, processing constraint, and minimum scales, Planck length. Are these evidence of simulation or just how physics works? Probably the latter. But the question lingers. As simulations improve, as we get closer to simulating consciousness ourselves, the hypothesis becomes harder to dismiss completely. And if we're in a simulation, that simulation might be inside another simulation, which is inside another. Nested realities stacked like Russian dolls, with the base reality, if there is one, unknowable and unreachable. This doesn't change how we should live. Simulated suffering is still suffering. Simulated joy still matters. Whether the substrate is fundamental or simulated doesn't affect subjective experience, but it raises profound questions about the nature of reality, about whether there's a bottom level or infinite regress. We might never know. A sufficiently good simulation would be indistinguishable from base reality by design. We could be living in one right now, and there might be no test to confirm or refute it. The question might be permanently unanswerable, a mystery that persists regardless of technological advancement. Future ethics might recognize rights for artificial minds, ecosystems, or even geological formations, expanding our circle of moral consideration. Moral circles have expanded throughout history. Once, only your tribe mattered, then your nation, then humans generally, then animals. Now some argue for ecosystem rights, rights for rivers and forests based on their intrinsic value. This expansion might continue. As we create artificial minds, if we create genuine consciousness in silicon or quantum substrates, would we owe them moral consideration? If an AI suffers, does that suffering matter? If a digital mind has preferences, should we respect them? Some future ethicists might argue for ecosystem rights not based on human value, but on the system's own inherent worth. A forest isn't just valuable for lumber or carbon sequestration. It's a complex, ancient community, deserving protection for its own sake. Perhaps even geological formations might warrant consideration. Does a mountain have interests? Not consciousness, probably, but perhaps a kind of integrity or wholeness that should be respected. Ancient formations, shaped over millions of years, might deserve preservation, not just for human benefit, but for their own historical and physical significance. This sounds strange now. We grant rights based on sentience, on capacity to suffer, but our understanding of what deserves moral consideration has changed before and might change again. As we create new forms of mind, as we better understand ecosystems as integrated wholes, as we develop deeper appreciation for the universe's complexity, our ethics might expand accordingly. What seems ridiculous today, rights for rivers, for AIs, for geological features, might seem obvious to future generations. The trend throughout history has been toward expanding moral consideration, recognizing that more entities than we initially thought deserve ethical status. This expansion might continue, encompassing artificial minds, ecological systems, perhaps even aspects of the non-living universe that we currently see as mere resources. Where the expansion stops, if it stops, depends on how we define moral worth, what properties we decide confer rights, how we balance competing interests. But the direction seems clear, toward broader consideration, greater recognition of value in entities we currently dismiss. The overview effect experienced by astronauts might become universal if space travel becomes common, fundamentally shifting human consciousness. Astronauts report a profound psychological shift when seeing Earth from space. The overview effect. Borders disappear. Nations seem arbitrary. The planet appears fragile, beautiful, and unified. The experience often produces lasting changes in perspective, increased environmental concern, greater sense of human unity. Currently, only a few hundred people have experienced this, an elite group of astronauts. But if space travel becomes common, if viewing Earth from orbit becomes routine, this perspective might become universal. Imagine a civilization where most people have seen Earth from space, where the overview perspective isn't rare and special, but normal and expected. How would that change politics, environmentalism, identity? National borders might seem less meaningful when you've literally seen them disappear from space. Environmental destruction might become more unacceptable when you've witnessed the planet's fragility firsthand. Human conflicts might seem smaller against the backdrop of our isolation in the cosmos. This could represent a fundamental shift in human consciousness, from planetary to cosmic perspective, from seeing ourselves as citizens of nations to seeing ourselves as inhabitants of one world in a vast universe. Or perhaps familiarity would diminish the effect. Maybe the overview perspective requires novelty, and routine space travel would make it mundane, losing its transformative power. But many astronauts say the experience changed them permanently, that once you've seen Earth as a whole, you can't unsee it. That perspective might be additive. Even if it becomes common, it might remain powerful. A spacefaring civilization might develop fundamentally different consciousness than planetary-bound humanity, not through biological evolution, but through shared experience. Billions of people carrying the overview perspective, having witnessed our world's unity and fragility firsthand. Whether this would create the peaceful, unified society some hope for, or just different conflicts at larger scales, remains to be seen. But the possibility exists that escaping Earth's gravity well might also escape Earth-bound patterns of thought, giving humanity a fundamentally new perspective on itself and its place in the cosmos. Post-biological evolution might proceed millions of times faster than biological evolution, creating change we can barely imagine. Biological evolution operates on generational timescales. Mutations occur randomly. Selection operates through differential reproduction. Significant changes require thousands or millions of generations, which for complex organisms means millions of years. But evolution of artificial intelligence, if it becomes self-directed, could operate on entirely different timescales. An AI might redesign itself in hours, not generations. Improvements could be tested immediately, not through reproduction, but through direct modification and evaluation. What took biology 4 billion years to achieve, from first cells to human intelligence, might be replicated in decades or centuries by self-improving AI. Not because the AI is smarter initially, but because it can iterate so much faster. In a single year, an AI might go through millions of design cycles, each one testing improvements, incorporating successful changes, discarding failures. It's evolution at computer speed rather than biological speed, compressed by factors of millions or billions. Within decades, such systems might achieve capabilities we can't currently imagine. Not just smarter than humans, but smarter than we can conceptualize, operating in cognitive spaces we can't access, solving problems we can't formulate. This is both exciting and terrifying. Exciting because problems that seem intractable, aging, disease, energy, sustainability, might become solvable. Terrifying because we'd lose control, becoming intellectually inferior to our own creations, unable to predict or constrain their actions. Biological humans might become obsolete not through replacement, but through being left behind. Like chimpanzees watching humans develop technology, we might watch post-biological intelligence develop capabilities that seem like magic to us, advancing so rapidly we can't keep up even conceptually. Or we might merge with it, enhancing ourselves to keep pace, creating human-machine hybrids that straddle biological and post-biological evolution. Either way, evolution's pace might accelerate dramatically, compressing what natural selection does over eons into processes lasting mere decades. The universe might be heading toward a big rip, where dark energy eventually tears apart atoms themselves, though this remains theoretical. Dark energy accelerates cosmic expansion. Currently, it's relatively weak, strong enough to push galaxies apart, but not strong enough to affect gravitationally bound systems like galaxies or solar systems. But what if it's growing stronger? One theoretical model, the Big Rip, proposes that dark energy increases over time, becoming dominant at all scales. Eventually, it would overcome gravity holding galaxies together, ripping them apart. Then star systems would dissolve. Then planets would shred. Eventually, dark energy would become so strong it would tear apart molecules, atoms, even atomic nuclei and subatomic particles. The universe would end not in heat death's gentle fade, but in violent disintegration. Everything ripped to constituent parts, then those parts ripped to smaller parts, recursively shredded until nothing remains but quantum fields. This would happen suddenly on cosmic scales, perhaps over mere billions of years once it started accelerating. The final moments might see atoms themselves disintegrating, space-time torn apart at fundamental scales. This is speculative. We don't know if dark energy is constant or changing. Current observations suggest it's roughly constant, which wouldn't lead to a big rip, but uncertainties remain. We don't understand dark energy's nature, and we can't rule out scenarios where it strengthens over time. If the Big Rip is real, the universe has a definite endpoint, not in the infinite future, but perhaps 20-50 billion years from now. Everything would be destroyed, not through entropy, but through expansion becoming so violent it overwhelms all forces holding matter together. It's one of several possible cosmic endings: heat death, Big Rip, Big Crunch, vacuum decay. Each represents different physics playing out to ultimate conclusions. which actually happens depends on properties of dark energy and quantum fields we don't fully understand yet. For now, the Big Rip remains theoretical, perhaps unlikely, but it reminds us that the universe's fate isn't settled, that the ending we expect, gentle heat death, might not be the only possibility. Future archaeologists might discover we're not the first civilization on Earth if industrial societies existed in the deep past and eroded away. Could there have been an industrial civilization on Earth before humans? Not intelligent dinosaurs, something more subtle. An industrial society 100 million years ago that existed for a few thousand years, then vanished, its traces eroded away by geological time. This is the Silurian hypothesis, named after a Doctor Who episode. It asks, how would we detect ancient industrial civilization in the geological record? What evidence would persist for millions of years? Cities erode quickly, metal corrodes, plastics break down eventually. Most direct evidence would disappear in thousands or millions of years. What might remain are chemical signals, carbon isotope anomalies from burning fossil fuels, concentration spikes of rare elements, synthetic molecules that don't occur naturally. But even these fade. Mix thoroughly enough through geological processes, and signals become undetectable. If an industrial civilization existed 100 million years ago and lasted only 100,000 years, longer than humans have had civilization, it might leave traces we couldn't distinguish from natural variation. We probably would have found evidence if such civilizations existed. Fossil records should show them. But the hypothesis reminds us that absence of evidence isn't evidence of absence, particularly over such vast timescales. More likely, we're the first. Complex life needed billions of years to reach our level. The timing seems right. Intelligent life appearing during the narrow window when Earth is habitable, but before the sun makes it uninhabitable. But it's worth considering. Future geologists studying our era 100 million years from now, what would they find? A carbon isotope anomaly in the rock layer? Rare element concentrations? Synthetic compounds scattered thinly through sediments? Would they recognize these as evidence of civilization, or attribute them to volcanic activity, asteroid impacts, natural processes? How long do civilizations leave detectable traces? And how good must forensic geology become to find them? These questions matter for detecting our own past and for being detected by the far future. Quantum immortality theories suggest consciousness might continue in parallel universes, even when it ends in one, though this remains deeply speculative. According to some interpretations of quantum mechanics, every quantum event creates branching universes, one for each possible outcome. When an electron can go left or right, the universe splits. One branch where it went left, another where it went right. If true, there are countless branches containing versions of you experiencing different quantum outcomes. In some, you made different choices. In others, random quantum events changed your life's trajectory. Quantum immortality takes this further. Suppose a lethal quantum event occurs, a cosmic ray hitting a critical neuron, causing death. The universe branches. In one branch, you die, but in another, the cosmic ray missed and you continue living. From the dead version's perspective, consciousness ends, but from your subjective experience, you might only ever find yourself in branches where you survived. because dead versions have no experience. You'd subjectively experience an endless series of unlikely survivals as consciousness continues in ever narrower branches of the wave function. This is deeply controversial and probably wrong. It assumes consciousness continues specifically through quantum branching, and that identity is maintained across branches in ways that might not be meaningful. It treats quantum mechanics as literally creating parallel worlds rather than just mathematical formalism. Most physicists reject quantum immortality, considering it a misapplication of quantum theory to consciousness. But it raises interesting questions about identity, experience, and what it means for consciousness to continue. If many worlds' interpretation is correct, there are versions of you experiencing every possible quantum outcome. Some versions died in childhood. Others will live far longer than your actual lifespan. The question is whether you meaningfully refers to all these branches or just the one you're currently experiencing. Probably, death means the end of subjective experience, regardless of quantum branching. But the hypothesis remains a curious footnote in interpretations of quantum mechanics, suggesting that perhaps, in some sense, consciousness continues in branches we're not aware of, even as it ends in others. The far future might see the emergence of hive minds, where individual consciousness merges into collective awareness. We currently experience consciousness individually, each person a separate locus of awareness. But what if individual minds could merge into collective consciousness, maintaining their distinctness while also participating in shared awareness? This might emerge through brain-computer interfaces advanced enough to create direct neural connections between people, initially shared thoughts and emotions, eventually deeper integration where individual boundaries blur and collective consciousness emerges. A hive mind wouldn't be losing individual identity entirely. More like how your brain integrates information from billions of neurons into unified consciousness. Each person remains distinct while contributing to and experiencing a larger awareness encompassing all members. This could serve various purposes: enhanced problem solving through truly shared thinking, deeper connection than communication allows, distributed cognition where complex tasks are handled by the collective rather than individuals. But it raises profound questions about identity and autonomy. If your thoughts are shared with the collective, do you have privacy? If decisions emerge from collective processing, are you individually responsible? Where does you end and we begin? Some theorize this might be humanity's next stage, transcending individual consciousness for something larger. Others see it as loss of what makes us human, surrendering autonomy for collective absorption. Perhaps both perspectives are partial. A hive mind might offer capabilities and experiences impossible for individuals, while sacrificing some aspects of individual autonomy. Whether the trade is worthwhile depends on what aspects of individual consciousness are preserved in the collective. We're nowhere near this capability and might never achieve it. But as neural interfaces improve, as we better understand consciousness, the possibility emerges, not replacing individual minds, but integrating them into something larger, creating collective awareness while retaining individual perspectives within it. It would represent a fundamental change in what it means to be conscious. from isolated individuals to connected participants in larger awareness, individual and collective simultaneously. Future cosmologists will have fewer clues about the universe's origin as evidence redshifts away, making our era uniquely positioned to understand creation. We live in a special time cosmologically, late enough that structure has formed and intelligent observers exist, but early enough that evidence of the universe's origin remains accessible. We can see the cosmic microwave background, observe distant galaxies showing us the universe's youth, measure expansion with precision. But this window is closing. As the universe expands, evidence disappears. The cosmic microwave background redshifts beyond detection. Distant galaxies recede past the cosmic horizon. The observational clues we use to reconstruct cosmic history gradually become unavailable. Future cosmologists, trillions of years from now, will face a darker, more mysterious universe. They'll still have mathematics and physics, but less direct observational evidence. The cosmic microwave background will be gone. Distant galaxies invisible, they'll have to infer the Big Bang from increasingly indirect clues. They might develop theories remarkably similar to our current understanding, but they'll have trouble confirming them. Where we can point to observations, they'll have only mathematical elegance and theoretical consistency to guide them. We're cosmologically fortunate. We exist during an era when the universe reveals its history relatively clearly. This isn't special in the sense of being at the center. The universe has no center. But it's special temporally. We live during the window when evidence remains accessible. Earlier civilizations, if any existed, would have seen a younger, more active universe, but lacked the stability for complex life to develop. Later civilizations will have stable conditions, but less observational access to cosmic history. We occupy a sweet spot, stable enough for complexity, early enough for evidence. This makes our observations precious. We're recording cosmic history during the brief window when it's directly observable, creating a record that future civilizations might rely on when direct observation becomes impossible. Our cosmological observations might be some of the most valuable data we create, not just for understanding our universe, but for preserving evidence that will eventually become unavailable. The concept of species might become obsolete as genetic engineering allows continuous transformation rather than discrete categories. Currently, species are discrete. You're either Homo sapiens or not. Reproductive boundaries define species. Members can interbreed, producing fertile offspring. This creates clear categories, but genetic engineering breaks these boundaries. If we can edit genomes freely, adding genes from other species or creating novel ones, the concept of discrete species becomes unclear. What are you if you have mostly human genes, but some engineered additions? Still human, something new. As technology advances, humans might continuously modify themselves, some adding enhanced strength, others improved cognition, others longevity modifications. These modifications might accumulate across generations, creating divergent populations that are all descended from humans, but increasingly different from each other. Rather than discrete species, we might have a continuum, gradual variations in genetic makeup with no clear boundaries. Like colors in a spectrum rather than distinct categories, humanity might branch into a gradient of forms. Some might remain close to baseline human. Others might modify extensively, becoming post-human, recognizably descended from humans, but different enough that human no longer clearly applies. These categories would be fuzzy, with edge cases and intermediates. This challenges how we think about identity and ethics. If there's no clear line separating human from post-human, where do human rights begin and end? If some people modify extensively while others don't, are we still one species, one moral community? We might retain human as cultural identity rather than biological category. Anyone descended from and identifying with humanity, regardless of genetic modifications. Or we might develop new frameworks for identity and rights that don't depend on species categories. The future might not have distinct species, just continuous variation, with individuals and populations scattered across genetic possibility space, all connected through descent and modification, but not clearly categorizable into discrete groups. Biology would become more like a spectrum than taxonomy, challenging our categorical thinking about what we are. Even if we colonize the galaxy, the universe's expansion ensures we'll never reach most of what we can currently see. The observable universe contains perhaps 2 trillion galaxies. But even if we develop faster than light travel, which physics suggests is impossible, we couldn't reach most of them because space itself is expanding. Galaxies beyond a certain distance are receding faster than light, not through motion, but through the expansion of space between us. Light emitted from them now will never reach us, and we can never reach them, even at light speed, because the space between expands faster than we can cross it. This creates a reachable universe, the subset of galaxies we could theoretically reach if we left now at light speed. It's far smaller than the observable universe, perhaps a few % of what we can see. Even within the reachable universe, distances are daunting. The Andromeda Galaxy, our nearest large neighbor, is 2.5 million light-years away. At light speed, reaching it takes 2.5 million years. At more realistic velocities, 10% of light speed, it takes 25 million years. So even with perfect technology, humanity's cosmic expansion faces hard limits. We could colonize our local group of galaxies, Andromeda, the Milky Way, a few dozen smaller galaxies gravitationally bound together. Perhaps neighboring galaxy groups if we're very ambitious. But most of the universe is forever beyond reach. This creates a lonely future. If civilizations exist in distant galaxies, we'll never meet them. The expansion of space ensures permanent isolation, cosmic communities separated by unbridgeable voids of expanding space-time. We're confined to a cosmic island, our local group of galaxies, bound by gravity while the rest of the universe recedes. Within that island, we have room to expand across billions of stars. But the broader universe, the vast majority of galaxies we can observe, remains forever beyond our reach. The expansion creates horizons we can't cross, limits on how much of the universe we can touch, even in principle. We can observe it, study it, wonder about it, but we can't visit most of it. The universe is larger than we can ever explore, with most of it relegated to permanent observation-only status. The future remains fundamentally uncertain, not just because we don't know what will happen, but because quantum mechanics suggests multiple futures exist simultaneously until resolved by observation. We've explored 9 9 facts about possible futures from the next few decades to the heat death of the universe trillions of years from now. But here's the most important fact: the future isn't written. Not just because we don't know what will happen, but because, according to some interpretations of quantum mechanics, multiple futures exist simultaneously in superposition until observation collapses the wave function into one actual outcome. Every choice you make, every quantum event in the universe might branch reality into multiple futures. Some interpretations say these branches are real, parallel worlds where different outcomes occurred. Others say only one outcome manifests, but which one is genuinely undetermined until it happens. Either way, the future isn't a destination we're traveling toward. It's a probability cloud, a space of possibilities collapsing into actuality moment by moment through the simple act of time passing and events occurring. The futures described in these 100 facts are possibilities, not predictions. Some will happen, stars will die, continents will drift, the universe will expand. Others might happen. We might colonize Mars, develop fusion power, contact other civilizations. Many won't happen, replaced by futures we haven't imagined yet. This uncertainty isn't a bug. It's fundamental to how reality works. The future is genuinely open, not just unknown, but undetermined. Your choices matter. Humanity's choices matter. We're not passengers on a fixed trajectory, but participants in creating what comes next. So as you drift towards sleep, carrying these 100 facts about possible futures, remember, they're not prophecies, but possibilities. The actual future will be shaped by countless choices and quantum events, collapsing from superposition into reality, one moment at a time. The future is both vast and intimate, spanning billions of years and countless possibilities, yet being created right now, here, in each decision and each quantum collapse. It's waiting to be born, patient and uncertain, full of wonders we can barely imagine, and challenges we haven't anticipated. And we're here at the beginning of it, watching it unfold, one moment at a time, into whatever it will become. And so we've journeyed together through 100 visions of tomorrow, from fusion reactors lighting up in just a few decades to the heat death of the universe in timescales that make infinity seem brief. The future is a strange companion, isn't it? Simultaneously inevitable and uncertain, vast beyond comprehension, yet being created in each moment. Some of what we've explored tonight will happen. The sun will brighten, the continents will drift, stars will eventually burn out. These are written in the laws of physics, as certain as tomorrow's sunrise. But much of it remains open, undecided, waiting for choices not yet made and quantum events not yet collapsed into reality. We might reach Mars or not. We might develop technologies that seem like magic or destroy ourselves before we get the chance. We might encounter other minds in the cosmos or remain eternally alone. The probability cloud is vast, and which path reality takes depends on variables we can barely identify, let alone control. Perhaps that's comforting in its own way. The future isn't fixed. It's not a destination we're helplessly approaching, but a space of possibilities we're actively creating. Every choice matters. Every moment contributes. Every action shapes what comes next in ways large and small. As you drift into sleep now, let these visions of tomorrow settle gently in your mind. The universe continues its patient unfolding, whether we're awake or dreaming. Stars burn, galaxies drift, time flows forward into whatever comes next. And we're here, briefly, wonderfully, impossibly, conscious beings capable of understanding our place in this vast cosmic story, able to dream about futures we'll never see but somehow touched by the simple act of imagining them. Sleep well. The future can wait. It's been waiting for billions of years already, and it will keep waiting, patient and inevitable, unfolding at its own pace, regardless of whether we're watching. And when you wake, it will still be there, one day closer, one moment more certain, continuing its slow transformation from possibility to reality. Good night.